Welcome to this morning section. After the lezione leonardesca of yesterday, we are back here, and we start with the first lecture of the course by Franco Flandoli. And okay, I think that you can start.
Thank you. Thank you very much. It will be an experience to speak with this very advanced audience of young people. And I hope to, even if I'm not so strong technically, I hope to give some interesting conceptual information. No, ecco, ho già sbagliato. Ho sbagliato. Ancora. E devo girarlo così. Okay, I identified three keywords that in the future I would like to mix up. I insist on the future because it is very difficult to mix these three and find a common logic around them. I start to have some intuition thanks to the works of many people, but I'm not sure that I can give you really deep information during these lectures. The only thing I would be aware, be advised that is not what I have in mind is not free lunch, not easy links, For instance, I grew up for 20 years thinking that regularization by noise and spontaneous stochasticity were linked by the Peano phenomenon. Okay, it's not completely wrong, but was really misleading and took me away from the right intuition for many years. Nowadays, there are works of the last 1-2 years by Alexei Malibayev and collaborators like the student Dmitry Bandak and collaborators like Theodor Drivas, in which they understood, or Jeremy Beck in Nice, they understood the spontaneous stochasticity in a completely different and much deeper way than the Peano phenomenon that I always had in mind. What I mean by the Peano phenomenon? I mean that if you consider this equation, consider this differential equation, x point equal to, for instance, to be more interesting, the sine of x, square root of absolute value of x, and add a small noise, time derivative of a Brownian motion. I don't want to enter in any detail now. So take this model with the initial condition x0 equals 0, and the picture is the following. The deterministic problem as, let me try to change the color, as the solutions that we know of the Peano phenomenon, namely the zero solution, something like t square up to constant n minus t square, and all the infinitely many others which branch everywhere. And if we superimpose noise, it happens that when we put noise, starting from 0, there are fluctuations of the noise, and after a while there is a sort of choice, and some other time the choice is below. And it happens that the law of the stochastic process, let me take this color, the law of the, if we take the stochastic process and its law on path space, this law converges weakly to 1/2 the x plus solution, the maximal solution here, delta, the delta Dirac in x plus 1/2 the delta Dirac in x minus. x minus. And therefore there is a spontaneous stochasticity in a sense of the deterministic problem, because from 0 with some probability nature maybe selects the two maximal solutions with equal probability, and the others are not selected. This example is clean. Unfortunately, almost no generalization to more dimensions or infinite dimensions, very clean, but the spontaneous stochasticity that I mentioned by Alex Malibayev, I'm sorry that every time it's possible that I spelled wrongly, and collaborators is completely different. And how the spontaneous stochasticity of Alexei is linked to regularization by noise is completely unclear. The link by regularization by noise, I forgot, is that this equation has a unique solution when there is noise. So with noise, this equation has unique solution, and so the noise regularizes, and in the limit, it selects something with spontaneous stochasticity. But the deeper concept nowadays is completely different, and so the link is to be understood. The link with convex integration is more difficult in principle, because apparently the two theories go in opposite directions. Regularization by noise seems to go in the direction of proving well-posedness thanks to noise, and convex integration to produce counterexamples to well-posedness and other phenomena. But working a little bit at the technical level, I cannot say that really there are similarities, but at least there could be a common story, a common portrait in which the two emerges from a certain picture. I'm not sure that I am ready now to communicate this in a good way, but this is my feeling, my purpose in the today, and I mean in these talks and in the next future to understand better the links. And the links of both of them with spontaneous stochasticity, of course, convex integration and spontaneous stochasticity are linked very easily by the word non-uniqueness, because if you want to have spontaneous stochasticity, you need non-uniqueness. The problem is that randomizing convex integration could be a program, but how to reach spontaneous stochasticity from convex integration is unclear today. Anyway, there could be in the future progresses on the link between these two. Thank you.
Just a
Yes.
question to understand the terminology.
Right.
When you say spontaneous stochasticity,
Hey.
You mean that you regularize with a well-posed problem,
Okay.
and in the limit you get a non-unique.
Okay, a friend told me this should be called induced stochasticity. Spontaneous stochasticity requires non-uniqueness and should be a selection of the non-unique solution with probability. And this selection should come from some procedure, which could be a regularization either by noise or by modifications. This is what I mean in general by spontaneous stochasticity. A non-uniqueness with a probability measure selected in a natural way by some limit procedure. You're right, I agree with you. But it's not specific of which approximation you have to use. Maybe different approximation, etc. could give different results. In a sense, with respect to non-uniqueness, non-uniqueness is set theoretical, spontaneous stochasticity is probabilistic, but with a vague, not well-defined intuition of universality of the probabilistic selection. Okay, like to make a comparison, if you take the concept of strange attractors, axiom attractors, hyperbolic, they have infinitely many invariant measures, but only one is the correct one, the physical one. And so also here there could be a non-uniqueness in which, however, there is a unique measure which, which is selected by some principle. Of course, it is not always true. It could be true for some problem and not for others. Since I will compare technically only convex integration and regularization by noise, spontaneous stochasticity will be only a few remarks, I would like to identify immediately, unfortunately, a technical difference because it's too early for me to give these lectures. I hope next year I could give more mature. The technical difference is, let me describe it and follow the slide. So let me start from the two-dimensional Euler equation on a torus, written first for the velocity and pressure, as usual, and then written for the vorticity, okay? U is velocity, P the pressure, omega is the vorticity. The vorticity satisfies a nonlinear transport equation because the U is related to omega by the Biot-Savart law. K is the Biot-Savart kernel that in full space is this one, and depending on the domain you have to put a certain smooth correction. This is well known. Now I will elaborate over this scheme. Of course there is something analogous in dimension 3, but you know, in dimension 3 the equation for the vorticity contains the stretching term, which is very complicated, and my understanding of what could be done here is very difficult due to that. So let me restrict to dimension 2. And assume that you apply a filter, like a filter could be lambda with lambda of we apply lambda to u, for instance. Lambda u of x could be the integral of a function x minus y u of y dy, okay, or Fourier, okay, some filter which matches the boundary conditions, the periodicity, and commutes with derivatives. And here I write the equation for the filtered variable lambda u bar is lambda u. I write this equation in two forms, because this is fundamental, unfortunately, for the division between let me anticipate, from here I go in the direction of regularization by noise, and from here in the direction of convex integration. And until now I was not able to reconcile this dichotomy. So sorry, as I say several times, these talks are a little bit too early with respect to the aim that I propose. So this is the classical Reynolds decomposition, in a sense, in which the Reynolds stress emerges, and this decomposition is less classical. If you write u bar plus u prime equal u, so if you rewrite this as u grad u, you immediately see that this is the typical mollification of the commutators. This symbol is the commutator. This symbol is the commutator, so it is u grad of applied to lambda u minus the filter lambda applied to u grad u. And also here, okay, and here there is a bar. So you see, this term is equal to this term, and this term comes from filtering the equation. This one is more classical, this is less classical. The advantage of the second one is that we see the effect of the assume that we interpret U bar as large scales and this as small scales. Small scales. Here we see the effect of the large scales on themselves and the effect of the small scales on the large scales. But there is this complicated remainder. And this is rigorous, namely from Navier-Stokes we can write this. But they open the path to two different idealizations. The first idealization is we start from this Reynolds type equation, we write R, and from now on we consider R as a variable or as a data, not like this complicated expression. So either we look for triples which solve this equation, or given R we look for solution UP of this equation. Okay? And this is the origin of the convex integration procedures. Okay? The other is the second. You remember there was the equation for the large scales, in which large scales act on themselves and small scales act on the large, plus the commutator. Here, in a sense, is more trivial. We delete the commutator because commutators are small, but in fact it's not true in this case. I cannot prove that they are small. So we delay the commutator and we look to this equation as an equation for this triple. So either a solution is a triple U, P, U prime. I miss the bar from now on. Now we have a new equation, a phenomenological equation. The meaning of U is large scales and the meaning of U prime is small scales, exactly like when in convex integration we see this equation. We think that U is larger and R is more oscillating. The same here. U is larger, slower, U prime is more oscillating, and either we look for a triple which solves, or we give a U prime and we look for UP. And this is, in a sense, almost the starting point for regularization. So I cannot really completely reconcile the two approaches. I tried, but I didn't succeed in a short time to repeat convex integration for this approach. I tried for a long time to do the regularization for the other, I never succeeded. I tried to repeat a convex integration for this in order to have them really parallel, but I didn't succeed in time, so maybe it's not possible. So, okay, there is a small difference in the starting point of the two theories. Sorry, I have to move this. Yes?
Why did the computer,
yes.
where did, I mean, why did it, in the second, when you say, not in that slide, yes.
Ah, sorry.
When you take that and you say it is idealized as, I mean, as below, I mean, the commutator, okay, mi sembrava.
I simply delete the commutator.
Okay, you delete it.
Yes.
Okay.
Yes,
Okay.
Above I delete the complexity of this operation, which unfortunately, I mean, when Reynolds wrote the same, U bar was a true average, it was not a partial average like a filter. And when it is a true average, you can work a little bit and show that this is nothing else than U prime tensor U prime bar, which has a very strong interpretation of the small scales mediated, and therefore is very clear that these Reynolds stress are the small scales inserted into the large scales. In this case of modifiers of Fourier is not completely true, so this is a very complicated expression that we transform in a given object. Oh, sorry, I forget always. I have to move here. And here we simply delay the commutator with the philosophy that commutators maybe are small sometimes. Okay. But there is still one more step. This story of the commutator I have to do at the level of the vorticity equation. This is why I introduced the vorticity equation above immediately, because the technology we have developed for regularization by noise has its own limitations, and also mostly because of interpretation. For me, understanding the vorticity equation is better than the velocity equation. So let me repeat. At the level of vorticity, we have a filter, lambda. So omega bar is the filter vorticity. Omega prime are the fluctuations of vorticity, small fluctuations. U bar and U prime are the Biot-Savart of the two, the velocity field associated to the large and small scales. Rigorously speaking, we could write this identity for the large scale vorticity, large opposite to velocity, in which drawing pictures for me would be a little bit complicated. When I move to vorticity, I at least maybe is certainly in my mind is an idealization, but I see bodies inside the fluid. There is the two-dimensional fluids. Inside the fluid there are bodies. So there are large rotating structures and inside the small rotating structures. So you have to think that there is a large body of omega bar, which is transported by the velocity field of itself, so it's deformed in the transportation by the velocity field of itself, but especially is deformed by transportation by the small scales. So this, let me change color. Let me try a more sophisticated picture. I have the small scales that are like small vortices. These are the omega prime or omega prime. And what happens that this omega prime by transport, they provoke a mixing of the large scale. So inside these large scales start to be rotation induced by the smaller. Or maybe you can think that this picture is outside. It's a little bit easier. So outside there is a small vortex which produces that there is a wing coming out from this large body. So it's very concrete to think about the effect of these velocity fields on the vorticity. It's really like bodies which are deformed by the action of other fields. At the level of velocity, I do not have the same intuition. And then, as I said, I delay the commutator and I take this more phenomenological equation in which omega u are the large scales and u prime is the small scales which act on the large. Exactly, and this is the starting point for the regularization by noise. Indeed, let me anticipate that is not only regularization, or not precisely regularization, but dissipation. Instead of regularization, more precisely, will be dissipation. A dissipation by noise, a phenomenon similar to mixing or dissipation by noise. And so you see, there are the Navier-Stokes. We rewrite the Navier-Stokes to summarize in, maybe it's summarized precisely here, or no. I come to this slide in a second. We start from the Navier-Stokes. We introduce filtered variables, large scale, small scales. We can write two kinds of equations rigorously for those, and then we can idealize this in two different ways. One a la Reynolds and the other a la Marchioro Pulvirenti, I would say, because I learned this strategy from Marchioro and Pulvirenti. What they did in the framework of point vortices, so you think you have in the two-dimensional domain you have point vortices, which means vorticity delta concentrated into points. In points, these xit are the coordinates, so xit are the positions of the point vortices, gamma are the intensities. What they did, they took, they approximated the point vortex dynamic by a dynamic of vortex patches. So let me. What they did is around each point they take a small ball at the beginning. At time 0 is a ball. So at time t equals 0, they take a small b epsilon, small ball around the initial position. I forgot the factor, the normalizing factor of this ball, so is divided by pi epsilon square. So they take an approximation of the delta Dirac around each ball, and then they observe the evolution of these vortex patches. And the evolution of the vortex patches can be described either as the evolution of the full vorticity field of these vortex patches together, the classical Euler equation, or as a sort of evolution of fat particles. So each vortex patch is transported by the velocity field of all the others, including itself. So at the end of the results, the key point is precisely the fact that here every vortex patch is transported by all the others, including itself. When they take the limit, when epsilon goes to 0, the interaction, the action of the vorticity of the velocity of itself on itself disappears. And so in the limit dynamic, each point vortex is moved by the velocity field of all the others and not by itself. The self-interaction disappears in the limit. In a sense, the theorem that they prove of convergence of this system to this system mostly is precisely to show that the self-interaction disappears in the limit, rigorously speaking. So I learned from them the idea of considering vorticity as decomposed in bodies, and each body is moved by the velocity field of all the bodies, including itself. Okay, which is precisely the same philosophy used here, where I have the large body omega moved by itself and by the small bodies. Okay, this is the motivation for this particular approach. Different from Reynolds. So this is the summary of what I said until now. Do you see the number of the slide somewhere? Yes, here. No, just to orient how much time I'm using. So the summary until now is that I want to compare these two phenomenological equation, the one a la Reynolds, which is the starting point of convex integration, and the one a la Marchioro-Pulvirenti, which is the starting point of regularization by noise. R and U prime are small scales, small, rapidly oscillating, and the other variables are the large. But in a sense, okay, I wanted to add the following remark, but it's not completely true. In the true Reynolds, U is strictly speaking large by definition, because the solution U of this a la Reynolds is the filtered large scales by definition. In the phenomenological, no more, because in the phenomenological we have replaced the true Reynolds stress by a new variable, so it's no more true. Here is no more true, very strictly speaking. Namely, we can take at time 0 the filter of the full solution. I don't know how to write the full solution. So there is a full vorticity field at the beginning. We filter and take the largest scales of this vorticity field, and then we make this evolution. But in this evolution, the solution omega does not preserve the property of being only the large scales, because as shown in this picture, it is strongly, the large scales are strongly affected by the small ones, and all these wings and wheels, they continue to be part of what we call omega. So omega at time 0 is made only of the large blob, but during the evolution develops wheels which are still contained in omega. Differently, oops, I forgot the trick. Which is the trick? Okay. I hope to recover in a second. Differently, if we, I made a mistake. If we consider Reynolds, apart from the fact that now we have replaced the true Reynolds stress by something artificial, in Reynolds you should be the largest scales by definition for all the time. So these two different viewpoints are not only mathematically two different viewpoints. In a sense, this is aimed to maintain the large scales affected by the small, and this is aimed to say, let's start large scale and let's see which modification the large scales are undergo. Okay? So it's slightly different. This was an introduction corresponding to the three keywords at the beginning, forgetting about spontaneous stochasticity. So I want to speak of these two topics together, regularization by noise and convex integration. The rest of the talk today is a sort of summary of regularization by noise, a beginning of the summary of regularization by noise, because we need elements of both theories. Okay, so I start from a regularization by noise that has nothing to do with convex integration, but historically was very important and is very important to distinguish categories of problems, and is the regularization by additive noise. I would say extremely misleading, exactly like the piano phenomena at the beginning. No, of course, it's a topic which is extremely interesting, but at the end produced that many people were stuck into questions which were not the right questions for 20 years. Me, de Bush, da Prato, and many others. Everything starts from a series of works, I name here a few people, which proved for ordinary differential equations in RD phenomena of restoring uniqueness by additive noise. Additive noise. So the equation speaks faster than the words. If I take an ordinary differential equation, B is the vector field in RD, and add a noise, additive noise, full, I've not written, sorry, yes, he's written here. W is a Brownian motion in RD, so the number of components of W is the same as the number of components of the solution. It's not degenerate, it's not acting on one component for a multidimensional problem. In this case, it restores uniqueness, also existence, for problems with extremely degenerate vector fields. This is the most celebrated results by Veretennikov, also because of the simplicity. B is just a bounded measurable function, forget about the equivalence class. So take a bounded measurable function, and if you add the noise, you restore existence and uniqueness in the strongest sense, in the strongest usual probabilistic sense. There are several ways of understanding both existence and uniqueness for stochastic equation. Talking about existence, there is the concept of weak existence and the concept of strong existence. But also the concept of path-by-path existence precisely for equation of this form. As Gianluca said yesterday, in equation with additive noise, you can just take one function, one path of the Brownian motion, so just one continuous function, and solve this equation, and then you put probability later. And this is what I mean by path-by-path. Path-by-path means take a path of the Brownian motion and solve this equation by some iterative procedure, and then you put probability on paths later. And so existence can be understood in three ways. Uniqueness also in different ways. The uniqueness in law, the pathwise uniqueness, and the path-by-path uniqueness. I don't discuss the weakest notions, uniqueness in law, because let's move to the strongest. Pathwise uniqueness means that if you take two processes, x1 and x2, which solve this equation, the two processes coincide. If I could make a comparison that this audience probably is like to say, if you take two flows that solve the deterministic equation, the two flows under certain assumption coincide. Path-by-path uniqueness is prescribe a single continuous function W, take all the continuous functions which satisfy this identity with this given continuous function, and try to prove that the set of such continuous function x is a singleton. There is only one continuous function which solves this, without probability. Path-by-path is without probability. So it's extremely strong, and in the comparison with flows, maybe it is close to say, try to prove uniqueness for a single initial condition instead of uniqueness of the flows. Sandy Davy succeeded to prove path-by-path uniqueness for this equation when B is L infinity. So in the case when B has no regularity to apply any kind of comparison between x1 and x2, still he was able to prove that for almost every path of the Brownian motion, this identity, considered as a deterministic identity, has only one continuous function which solves. So it's extremely strong. So the meaning of existence and uniqueness is extremely strong for this problem. The regularization produced by additive noise is extremely strong. It is so strong that everybody thought that this was regularization by noise. Regularization by additive noise is a synonym of restoring uniqueness. Yes, this was a wonderful story for decades, which perhaps was a little bit limiting the understanding of deeper phenomena. But since it is very beautiful, I want to show a modern proof. I'm sorry that many of you know this proof maybe, but I like to do it because it is used in papers, recent works by some of you. So the proof I'm going to explain is not under the very general assumption of Veretennikov, because they require additional tricks which are not trivial. So let me put myself in this slightly more regularized setup, continuous in time and elder continuous and bounded in the space variable. And I use this celebrated Ito Tanaka trick. I was so surprised to see that exactly with this name was used in one of your papers, the Ito Tanaka trick. Ito Tanaka trick starts from the parabolic equation called the Kolmogorov equation, in which you have all the ingredients of the stochastic equation. In the stochastic equation there was the noise, and the noise here corresponds to epsilon square over 2 Laplacian. There was the drift B, which corresponds to the first order operator, like in the link between characteristics and the transport equations. Time derivative, of course. The strange elements is that is backward, so we are, but this is not so strange also, you know, of course, characteristics and PD go the other way around, so it's not so strange that it is backward. So we have a final time condition, which we take 0. And the most strange thing is that we use a forcing term in the parabolic equation, which is the drift itself. And this penalization has a minimal role, but I will describe. So forget about this penalization for a second. There is this drift. When we discovered this trick around 2009, we were enthusiastic. We discovered following an idea of Tanaka. And then we realized that in the theory of homogenization, it was used for decades under the name of cell equation. So, okay, very difficult to discover new things in mathematics. But we didn't know. We discovered years later that was that. This equation was already used in the theory of homogenization. Is very powerful for understanding oscillations. Under the assumption that under this assumption, continuous, elder continuous, this equation has very strong solutions. This result is not maximal. I wrote what I need. I need this. The result is stronger. There is maximal regularity. So there is the second derivative is alpha elder, like the data datum. But I just need C12 for to apply Ito formula and also for a certain estimate. We see C12 bounded, so also the second derivative is bounded. And also I need the first derivative also is bounded, but I need the first derivative is small, and this comes from the zero initial condition and this extra damping. So if we put a strong damping, we can keep small the solution up to the second derivative excluded. The second derivative cannot be small because it's by compensation, but if you stay below the second derivative, all of them are small for large lambda. And this is a classical result. Use this classical result to prove the pathwise uniqueness under this simplified assumption, with the Ito Tanaka trick, or if we want, the Ito Tanaka Kolmogorov, that they remove the drift. Together, Ito Tanaka and Kolmogorov remove the drift in the following way. Take a continuous adaptive solution, because our aim is uniqueness. Okay, so we already have solutions. Take a solution. The solution satisfies the differential equation. If we compute U composed with the solution, classical computation we do also between transport and characteristics, some term disappear when we do the computation. Some term disappears thanks to the fact that X solves the characteristics. And here disappear. When you do the computation, there is the time derivative of U, the gradient of U, and in Ito formula there is also the Laplacian of U against the object created by X, which are precisely precisely the left-hand side of the Kolmogorov equation. And so altogether they are equal to the left-hand side, okay? Left-hand side. And so the left-hand side is here. So this time derivative is just the left-hand side of the Kolmogorov equation. In addition, when you do the gradient of u and multiply by the differential of x, there is the gradient of u multiplied by a piece of the equation. In the differential of x, there is also this piece. So there is this additional piece which does not appear in the Kolmogorov equation, the martingale of the problem. And the Tanaka viewpoint, which is also the viewpoint of homogenization, we understood later, Tanaka viewpoint is to use this kind of identity to understand integrals of this form. So we integrate this and we isolate the integral of B. This is very powerful. Let me explain more generally than this identity, but this identity is a wonderful example. You can put in place of B a delta Dirac. You can ask yourself, can I integrate the delta Dirac over a function x? And the point is take a delta Dirac, put the delta Dirac here, and try to have a solution of the parabolic equation equal to the delta Dirac. Then by this trick, you apply the chain rule. By this trick, the integral of the delta Dirac over the process is given by an expression. And the advantage of this strategy is that here you have a very regular object, and here we have a more regular object, because the solution u of the parabolic equation is more regular. Remember, B C alpha in space, the other properties, u, the gradient of u is C1 alpha. So gradient of u is, and u much more. So I mean, you replace an integral with the expression with much more regularity. And Tanaka used this. The reason of the name Tanaka is because Tanaka used this trick precisely to do the integral of the delta Dirac at x minus a Brownian motion. And it is possible to give a meaning to this object, even if a priori is very irregular. And the meaning of this object leads to the concept of local time. And so we copied this idea here, and it was successful. But then we discovered that in homogenization it was already used, because it's very good to understand integrals of this form when there are very fluctuating, rapidly oscillating fields. Okay. And then what we do now is we replace this integral in the stochastic equation by all this stuff. So replace this integral by this stuff inside the stochastic equation, the original stochastic equation, and get a new equation. So the original equation with the bed drift transforms into an equation more complicated, but with smooth coefficients. This part is absolutely trivial. U is a C2, so it will be handled very trivially by classical methods. This part will be handled by Ito calculus, again using that the gradient of U is smooth enough to handle this part. I collapsed some term into a function of initial condition. The initial condition appears in two pieces. I collapse in a single function. Only this term is disturbing, because this term is not of integral type, and so we cannot apply Gromwall to this term. So when you compare for uniqueness, you compare two solutions. You take two solutions and you compare. And it's good, the integrals are good when we do Gromwall, but this part is bad. part is bad. And so it is here that we need the gradient of u is small. If the gradient of u is small, this is contracting, is a contracting map, and so it's good. And this is explained here, extremely simple. Now we do a classical comparison of solutions. So we take two solutions. Two solutions, to be precise. What are two solutions? They live on the same probability space, so there is a probability space. These are two processes, so they are function of time, but also of the variable of the probability space. Both of them adapted to the same Brownian motion, and they start with the same initial condition, but I like to play with two different initial conditions for later use. And they are continuous. The paths of this solution are continuous. So each of them satisfies the identity that I just wrote a second ago, where there is the initial condition, there is this thing that will contract, this easy term, and the term which requires Ito calculus. So first, before Ito calculus, we just take norms. There is a where M is this. So different of if the initial condition is the same, this is already 0. This part, the part which comes from the difference of this as the constant related to this constant, you remember the gradient of u uniformly in space-time was bounded by this constant C lambda, which appears here, that is small, for instance, smaller than 1/2, and so this is solved, this is easy, and the stochastic part, you know, we cannot put norms inside the stochastic integral, so I still have to take the norm outside of this stochastic integral and then apply Ito calculus. And so I just copied the same inequality, take C lambda less than 1/2. So if C lambda is less than 1/2, we put this term on the other side, and we recollect. Recollecting, this difference is smaller than 0 if they are the same initial condition, plus this, plus with some factor 2 here, there, with this part. And now, okay, is this erasing at power 2 is not necessary, but erase the same at power 2. Erase the same at power 2, and then take expected value finally. Because the expected value of the square of this integral, stochastic integral, is particularly nice. Here I didn't write the beginning of the computation, I already wrote at the end of the computation. You bound with the second derivative of u and this term. Without expected value we cannot do anything, but with the expected value we reduce things to acceptable calculus. And therefore at the end, this is the end of the story, that the expected value of the square is bounded by 0 plus an integral of the expected value, and therefore by Gromwall we have this inequality. So this is 0, and therefore x1 and x2 at every time are in the same equivalence class, which has a name in probability. These processes are versions of each other, and since are continuous processes which are versions of each other and continuous are indistinguishable, so they are exactly the same process up to a single probability 0 set. And this is the proof of the pathwise uniqueness in this case. The proof of the path-by-path uniqueness by Davies is extremely complicated, another level of complications. Let me mention that, let me check time, let me check time a second. Let me mention that there are many generalizations. very interesting is this generalization by Krylov and Rechner, in which the drift, instead of being L infinity or Hölder, is LPLQ. You know that when there is equal, this is the famous Ladyszenskaya-Prodis-Serrin condition. The equal was excluded by this theory for many, many years, but around 5 years ago we understood how to approach the equal. I collaborated to one paper, but then a lot of other people made better. Krylov himself wrote 5-6 papers on the case P equal D. So this part of the theory was very important for probability, to try to understand all these tricks of probability, how they work, etc., etc. So just to mention, that was an important piece of probability theory. But of course, and there are infinite dimensional extensions of this. Infinite dimensional extension means something like dx equal to ax dt linear, Laplacian, plus bx dt. This is the analogous of the weak drift, Rath, plus dw, in infinite dimensions. But essentially, this generalization were more or less the same as the results above. Namely, for instance, typical with D'Aprato, we wrote a paper in which B was C alpha bounded on a Hilbert space, So precisely the generalization of the strategy that I showed you a minute ago. Namely, thanks to the fact that Giuseppe D'Aprato wrote, wrote a lot of books on Kolmogorov equations in infinite dimensions. Using the culture of Kolmogorov equation in infinite dimension, it was possible to generalize precisely the proof that I showed you, and prove that in infinite dimensions we have a pathwise uniqueness for problems like that. And then, together with Veretennikov, with Enrico Priola, with Michael Rechner, we tried to extend, but this kind of infinite dimensional extensions are very far from fluid dynamics, namely are always, they contain always assumptions on the drift which have nothing to do with the fluid dynamic equation. So that line of research, additive noise, restoring uniqueness, works fantastically in finite dimension. I didn't mention that you can do even distributional drift. The B here can be a distribution of a certain class, of course, but you can reach distributions and still have uniqueness. But when we move to infinite dimensions, we repeat results of the same nature, and the same nature has nothing to do with fluid dynamics. This is the point. D'Aprato and Debush wrote a great paper related to three-dimensional Navier-Stokes equation, Kolmogorov equation, an infinite dimensional Kolmogorov equation associated to three-dimensional Navier-Stokes equation, but even if the result apparently is very strong, it doesn't pay. It was not possible to repeat strategies like that one and use this Kolmogorov equation to prove uniqueness. At the same time, Martina Hofmanova and other people proved that a certain convex integration technique developed in the deterministic case extend to stochastic equations. And so at the end of the story, I do not believe anymore that additive noise may regularize three-dimensional Navier-Stokes. If I should beat, I would say no. I would not beat for the hope that three-dimensional, that additive noise proves because restores means if you know that there is. Okay. Now we know almost that there is non-uniqueness or weak solution. So the question whether additive noise proves uniqueness or weak solution, I think, is not correct. Is not the right way of trying to do regularization by noise for three-dimensional Navier-Stokes. This is my opinion now, but I work on that in that direction since 2008 or even before, until not so many years ago. So it was a sort of deviation due to these beautiful results in finite dimensions. It was not the correct viewpoint, probably. Indeed, additive noise and stochastic additive noise in Navier-Stokes could be linked to the intrinsic stochasticity problem, but not today. Not today. Let us move to transport noise. Around 2008-9. No, sorry, when I said that I started to work on uniqueness by noise, by additive noise for Navier-Stokes, I was wrong. No, it was not 2008. It was in the last century. I wrote a paper with Romito on Caffarelli con Nirenberg theory for three-dimensional Navier-Stokes, stochastic, in 1998. So really it is 20 years that I tried all possibilities, Caffarelli con Nirenberg theory, Kolmogorov theory, etc., to try to prove that additive noise proves uniqueness of weak solutions. Really a wrong research program due probably to these outstanding results in finite dimensions. Let us move to another kind of noise, transport noise, which is, you will see, is more promising. And the idea, let's go back to this inequality that I wrote before. Take two solutions of the ordinary. These are solutions of dx equal bx t dt plus dw, or epsilon dw, whatever. And we proved this inequality, but when this is zero, that also is zero, up to a constant. But now take two different initial conditions, so this is not zero, still the inequality is true. With a little more work, you have to use not the isometry formula of stochastic integration, but certain dupes inequalities. You can prove the same for every p. And when you have, an inequality like this with respect to a parameter, now the initial condition is a parameter. When we respect, and this is a random field, this is a random quantity depending on this parameter. When you have a random quantity depending on parameter, and in the parameter you have this kind of bound, you can try to apply Kolmogorov. I forgot to write Kolmogorov criterion or test. Some people call test, Kolmogorov test. Kolmogorov test requires that this number is greater than the dimension of the parameter. But when you have the freedom of p can be greater than the dimension of parameter. And Kolmogorov test says that when you have this with p greater than the dimension, there exists a modification which is continuous. Namely, the map from the parameter to the random field is a continuous map omega by omega. Omega here I mean the random parameter, not the vorticity. Omega by omega, this map is continuous. So it defines what is called the stochastic flow. So a continuous map from Rd to Rd, parameterized by time and by the random parameter omega. Stochastic flow associated to the SD. So the same computation that I did before based on Kolmogorov Ito-Tanaka trick is not trivial computation. The same computation based on Ito-Tanaka trick produces the existence of a stochastic flow. In fact, with Massimiliano Gubinelli and Enrico Priola, under this assumption that I used before, we have proved that this flow is a stochastic flow of diffeomorphisms. So associated to an equation with a drift which is only Hölder continuous, there is a stochastic flow of diffeomorphisms. These two items are to say why is natural to believe. First, because this Kolmogorov test prescribes that your flow is not only continuous, but is Hölder continuous, with Hölder exponent related to the p and the dimension by this. But since p is arbitrarily large, this ratio is reaches almost one, not equal, but almost 1. So for Hölderianity up to 1 is free from the previous computation plus Kolmogorov. But then if you write the equation for the derivative of the flow with respect to the initial condition, the equation for the derivative, at most it contains a second derivative of u, which were continuous, bounded, etc. U is always the solution of the Kolmogorov above. So this is again the same identity I've used before, but I've written for the differential of the flow. So always by the regularity of the Kolmogorov, you also deduce differentiability of the flow, and the fact that it's an invertible, etc., is more work. And so there are very strong flows. But when there are strong flows, clearly the idea is that the method of characteristics should allow to solve transport type equations or continuity or certain advection vector advection equations. And we did many of those cases. This is an example, again with the same authors. We took the transport equation, linear transport, under the same assumptions as before, plus a little bit to handle commutators, transport equation with transport noise. So the gradient of the solution is multiplied by the velocity field u, large scale if you want, slowly oscillating, and a fast oscillating part of additional velocity. And for this transport equation, we have uniqueness of weak solution in the class L infinity, for instance, in the class L infinity. And this was a little bit a striking result, in a sense, again, producing a lot of generalization attempts. And highlighting that for partial differential equation close to fluid dynamics, transport noise seems to work much better than additive noise. So transport noise maybe is much better than additive noise for equations which have fluid dynamic flavor. But the story is that, unfortunately, that in spite of the research for that result was 2010, and really a lot of researchers work on this subject from all over the world. Nobody was able to extend to nonlinear case. So the linearity of that equation seems to be essential to apply those kind of arguments. There is even a simple counterexample that I describe here. But let me mention that we and other people, we developed a lot of strategies. I described above the strategy based on stochastic flow, which is the natural one. By the way, curiosity for experts of transport equation, that since this stochastic flow is diffeomorphisms, automatically it means that the stochastic transport equation preserves a certain level of regularity. So it's not only uniqueness or weak solution, but also preservation of certain class of regularity, which is less common because, of course, all of you are comparing with the great results for deterministic transport transport equation by Luigi, Di Perna-Lyons, and many others. But the point is that preservation of regularity is not a typical result of the theory. Here comes from the smoothness of the stochastic flow. So really very rich, but extremely linear. Stochastic flows, using the concept of renormalization of renormalized solutions, we discovered another strategy to prove the same result, and this was the strategy to approach P equal D, let's say, the Ladyszenskaya Prodi-Serrin condition. There is another strategy based on the so-called chaos decomposition, the Malevin calculus, but no one extends to non-linear problems. All of them are limited to linear problems. And the key is that the drift must be deterministic. If the drift is random, as it is in nonlinear problems, because in nonlinear problems the drift depends on the solution is random. So when we move to random drift, all techniques fail. And the intuition, there is an intuition behind the technology. I mean, I could explain why in the technology of stochastic flow B random cannot work, but I just confuse, I just had too many information. If you want to know, just open and close the window. You have the Kolmogorov equation in which you put B, the drift, but B is random. B is random. But unfortunately, you have to solve the Kolmogorov equation backward in time. So the solution of the Kolmogorov equation depends on the randomness globally in time. So in a way that we call anticipating, is anticipating. And so when we move to the next step in which we apply Ito formula for the Ito-Tanaka trick, the Ito formula for anticipating the fields is completely different. There are new terms, it doesn't work. And if I describe you the renormalization, I can point where I cannot use B random in the chaos expansion, where I cannot put B random, and so on. So unfortunately, moving to nonlinear cases was terribly impossible and very strange, because usually when you have a linear theory by perturbation, you can do something, at least something nonlinear. There is even a simple, okay, but I wanted to say which is the intuition behind that. The intuition, apart from technologies, is that when B is deterministic, it has a certain singularities in its roughness. Very difficult to appreciate what does it mean, but it has singularities with roughness. And the additional Brownian motion of the equation moves inside these singularities, producing some kind of averaging. In fact, the concept of occupation time of the trajectory of Brownian motion, because at the end a single trajectory regularizes. It's not a regularization in probability. We are never taking expected values. So single trajectories of Brownian motion produce a regularization. So it is the occupation measure of trajectories, so that is like a pencil which moves and put ink on the plane. The occupation measure of the trajectory is quite diffused. So the single trajectory of Brownian motion is acting almost like a mollifier over the vector field, a fractal mollifier. So this is the intuition. But if the vector field is random, unfortunately, the randomness of the vector field and the randomness of the noise would match, and they don't produce anymore the regularization. The singularities of the vector field and the singularities of the noise could don't average the singularities of the vector field which move with the noise. And this is precisely what happens in this simple counterexample. In this simple counterexample, we have the two-dimensional Euler equation, and we add this the same noise as before, the same that produced the regularization above. And the result is the following. Assume that U is omega in U is a solution of this nonlinear problem, random. Transform this way. This is a it is like a random Galilean transformation. So you know that equations of fluid dynamics are invariant by Galilean transformation. So even if you don't read the computations, just by the fact that there is invariance by Galilean, you understand that this transformation will move into an equation of the same nature. In this case, equation without noise. So you can transform this equation with noise in this equation without noise just by shifting the position in a random way. And so this shows that we cannot hope of any improvement of regularity, uniqueness, etc. here, because everything can be transferred. If we have uniqueness here, we have uniqueness here, and vice versa, etc. So the fact that this noise is not able to regularize nonlinear problems, unfortunately. I hope it's the end. Yes, but this afternoon I have another talk. I can tell you how to do. This doesn't work, but there is something else which works. And let me say the summary and outlook. So the purpose of this lecture is to start a discussion of the link between regularization, dissipation, let's say, more than regularization, dissipation by noise, convex integration, and spontaneous stochasticity. There are these two starting points which are different, unfortunately, but they have something in common, different but not so different. I show that additive noise restores uniqueness in classical regularization by noise, but doesn't work for Navier-Stokes. Still, if we move from additive noise to transport noise, linear equations are very well treated. I call simple transport noise the noise that I used above, Brownian motion. This is a simple one. It doesn't work for nonlinear one, but we will see that more sophisticated noise, not that simple, can work in some case. I will see this afternoon. Thank you. This is the end of this slides.
Okay, thanks for
Thank
this.
you.
So are there questions?
So the case where B is Dirac delta, I mean, was not, was a generalization of that result from Verennikov?
No, the case B Dirac delta was Tanaka. Tanaka wanted to define the local time. I don't matter what does it mean. And the idea of Tanaka was define the integral of a delta applied to the Brownian motion. By the way, if you take the integral of a delta, it's an interesting exercise. Take the integral of a delta Dirac over a smooth function, f of t, in dt. Try to define in a reasonable way, like modifying the delta and send to 0. And this meets troubles when the function f has a maxima and minima. Because here, every time there is a stationary point, the occupation measure of this function, even if it is in one dimension, is like a function which moves a point. When there is a maximum, the function slows down and restart. It's like a curve which is not a regular curve. Slow down and restart when there is a maximum. When it slows down, it puts a lot of ink in that point, and the delta weights a lot of ink, and it doesn't work. When you move to Brownian motion, Brownian motion is a fantastic object with maxima and minima everywhere, but they are so many and so well distributed statistically that this doesn't happen. The Brownian motion never put a lot of ink anywhere. I mean, it distributes inks in a very regular way. So the occupation measure of Brownian motion is extremely smooth in any dimension, And so you can apply delta Dirac without too much pain.
Okay, so it's Tanaka who basically defined
Tanaka.
it in a regularizing it some way, and proving that there was some.
Right. The idea was exactly to use Tanaka had solved the equation delta U equal delta Dirac, and use the solution of this equation, Ito formula on the solution of this equation, so to speak. To do the same trick that we have used, not on the capital U solution of the big Kolmogorov that I showed, but solution of this simple Kolmogorov equation produced what Tanaka did.
Okay, other questions, remarks?
So one of the, say, key ideas of convex integration is that you can add the small scales and perturb with a small term with a lot of small scales the vector field in order to reduce the Reynolds tensor. Is there some, say, idea in this direction also in what you do in
the sophisticated noise that I will introduce this afternoon goes precisely in that direction, exactly, of modify the noise. Instead of being Brownian motion, will be something space-dependent with smaller and smaller scales. Will be precisely in the same direction. So there will be a comparison between this strategy with noise at smaller and smaller scales and convex integration, and with different outputs, but maybe sooner or later some people will merge a little bit the two theories.
Thank you.
Okay, other questions?
So one of the difficulties I think about studying the long-time behavior for two-dimensional Euler is its wealth of steady states, right, everywhere. And I think one of the benefits, right, of putting transport noise on two-dimensional Euler is that it should destroy most of those structures. Do you have any indication, or do you believe that putting transport noise, let's say suitably smooth, could actually restore uniqueness of some stationary measure for Euler?
No. I completely agree with the intuition, and I don't have any rigorous information. What we did, for instance, numerically, is to analyze what happens to two blobs of vorticity in 2D when they are sufficiently close and they merge. They merge very fast in a single blob with wings. We did it approximating the blobs by point vortices. So if we approximate the two blobs with 100,000 point vortices and 100,000, we see all the pathologies of the convergence to equilibrium of Euler, namely inside this single blob there are regions with no vorticity and so on. We don't know if sooner or later they will disappear and create a single stationary state in the limit. If we use 100 point vortices and 100 point vortices, when they merge, they construct a sort of universal shape. So I completely agree that a transport noise should give the necessary dirtiness to create a single shape, but I don't know any result.
Okay, other questions? Okay, so we thank the speaker.
Today we'll start talking about non-uniqueness, and we're going to try this setup, which feels more tame because I'm seated. Okay, so we'll give it a try. This time we'll talk about self-similarity and non-uniqueness. All right. I think my handwriting will improve in the course of the talk as I practice. So last time we talked about self-similar singularity formation. We talked about 3D Navier-Stokes. There is no self-similar singularity formation. And then we talked about Then we talked about burgers, and we classified all the self-similar blowups for which the blowup profile is for which the similarity profile is smooth. And we talked about also perturbing what happens when you try to add viscosity back in. So ideally, when you're studying non-uniqueness, there are kind of two non-uniqueness scenarios to keep in mind. One is first blowup, then non-uniqueness. That's one of the ideal scenarios, which you'd like to study for Navier-Stokes, and you'd like to study for Euler, but you don't know how to prove that Navier-Stokes blows up, so you can't study the continuation past blowup. And you don't know, okay, and we know some things about Euler blowup, but it's really new. Okay, so there's, Tarek's C1 alpha results, and there's this smooth boundary blowup with computer-assisted part, which no one can necessarily vouch for yet. Okay, so for those Euler blowups, it's not known, even for the C1 alpha stuff, it's not known how to continue past the blowup. Interesting problem. All right, so what we're going to do is talk about Navier-Stokes for now, and we're going to take the perspective that if you had a blowup, then any reasonable continuation should be a suitable Leray-Hopf solution. So, so what's the picture? The picture is something like, which if you've seen my talks, you've seen me draw many times. So here's the initial time. Okay, and here's time t star, which is the time at which smoothness is first lost, let's say. At this time, so in this region here, which is blue, if you start the evolution with some nice initial data, let's say H1, then in this blue region, the solution is smooth. And at time t star, that's when the solution, let's say, loses smoothness. We don't know whether that can happen. Here, you would need to have at least one point singularity. There really needs to be a point where the velocity wants to travel, where the velocity wants to be unbounded and particles want to travel with infinite speed. And then when you continue up here, so you continue as a suitable Leray-Hopf solution. And you don't know whether the continuation would be unique, but anyways, the continuation is necessarily, you can always pick a continuation which is a suitable Leray-Hopf solution. So you can just ask this, you can just ask the question, you just ask this milder question: are suitable Leray-Hopf solutions unique? Or if that's some crazy terminology that you don't like, just say, are weak solutions unique? But you have to be a little careful. We know weak solutions aren't unique because of convex integration, but okay. So you can ask this question: are suitable Leray-Hopf solutions unique? So again, there will be typed lecture notes, but they might not be out for a few weeks. So, by the way, let me just let me say what this let me say what this notion of solution is. So so you take some initial data, which is an L2, and it should be divergence free. So we're going to also consider the forced problem. So what's a good class for the force? A good class for the force is L1 time L2x. And you can make it as general as this: L1 time L2x plus L2 time H minus 1x. Because that's dual to where the velocity should live. The velocity should live in L infinity time L2x intersect L2 time H1x. And let's also just say that this is on some finite time interval. And you further assume that the initial data is obtained strongly at the initial time. So ut minus u0 in L2 converges to 0 as t approaches the initial time. Okay, and then we need to say something about energy. That's what this word suitable. That's where this word suitable comes from. Actually, this name suitable. It sounds really made up. Like, what should we call the solution? I don't know. It's suitable for the analysis that we're doing. Let's just call it suitable. And I made this comment in a talk at NYU. And Bob Cohn, who introduced the name, was in the audience. So I just asked him, "How'd you come up with this?" And he said it was basically like that. Just, it's suitable for what we're doing. Let's just call it suitable. Okay, so I need to say something about energy. All right, so it's enough to put this local version of the energy inequality. This is called the local energy inequality, and Hyunju is going to use it in her talk, so better introduce it now. Equals U dot F. So let me put less than or equal to. This inequality is supposed to hold in the sense of distributions, meaning you multiply by non-negative test functions. Okay. And then this local version of the energy inequality actually implies the global version. So if you just take the test functions on larger and larger balls, if you take them sharper and sharper in time, then you get the local version, or you get the global version of the energy inequality. So again, that'll become relevant in Hyunju's talk. So we're interested in this question of, okay, are these suitable array Hopf solutions unique? And it's kind of like starting from this time. It's like you can ask this question where you impose data which is singular, and we're going to pick that singular data, and for part of the talk we'll let ourselves also have a singular force, but anyway, it's like starting here. All right, those pictures are tantalizing. We'll look at them later. So we're going to discuss this. We're going to discuss that question in two settings. So in two settings, we're going to discuss it in the unforced setting, f equals 0. That's work of Jia and Schwerak. Also Julien Guillaud. So let me just say Jia, Schwerak, Guillaud, which I'll explain in some detail. And in this setting, the answer to the question is probably no, meaning that there's a numerical part, which is not actually a proof, but which is highly suggestive that the answer to the question, are suitable array Hopf solutions unique without force, is probably no. And then we'll talk about, F when you include force. This is work of myself with Elia and Maria. And then the answer is definitely no. Okay. So I'll state our theorem just so that we have it. So sorry to switch slides like that. So here's our theorem. So there exists F, and F is in a lot of spaces. I'll put it. I'll just put it in this one. Notice I'm writing intersection, not plus, and it's going to be in better spaces than this. Okay, there exists F and two distinct suitable Leray-Hopf solutions to the Navier-Stokes equations with identical body force F and initial data which is actually 0. Okay, so 2 comments. First comment is that the construction is actually at critical regularity. The construction is actually at critical regularity, meaning that if you were to make the force just a little smoother, so in fact our force is in L1 time L3 minus epsilon x for every epsilon. If you were to make the force just a little bit more regular, then all the solutions would have to, there'd be a strong solution, and all the solutions would have to agree with it. So the construction is really borderline, and in order to get Luray-Hopf, there's a big gap between getting Luray-Hopf and getting critical, because Navier-Stokes is supercritical. So, anyways, so the construction is borderline, and the other thing is we also have this gluing construction, which lets you put this non-uniqueness scenario into bounded domains, and also the torus. And the point of that is basically just to demonstrate that the non-uniqueness is local. It comes from, it's arising out of this self-similar solution, which is singular at the space-time origin, but then after the initial time, it instantly becomes smooth and things are kind of spreading out. But the singularity is really local, and therefore you should be able to glue it. The boundary conditions that you're putting out here shouldn't matter. So these are 2 comments. Okay, eventually I want to touch on Euler, and in Euler we can ask the same we can also ask these 2 questions, for unforced and forced. And the answers are, again, probably no and no. But I'll touch on that later. Questions or comments? All right. So let's talk about forward self-similar solutions. The kind of self-similar blow-up that we were talking about yesterday, sometimes that's called backward self-similarity because the solutions live for all negative times, and then they blow up at time t equals 0. We're going to start with singular data at time t equals 0, and then look for self-similar solutions that live for all forward times. They live for all positive times. So the ansatz is this one. Capital U, which is a function of x over root t, comma log t. So remember, this is called xi, and this is called tau. And those are our similarity variables. So you rewrite Navier-Stokes in these variables. You get d tau capital U minus 1/2 u plus xi dot grad u minus Laplace capital U plus u dot grad u plus grad capital P equals either 0 or f, or some capital F. So the scaling for capital F, the scaling for the force is like this. 1 over t to the 3/2, capital F, let's say like this. Okay, also divergence U, capital U equals 0. And remember now tau goes all the way to minus infinity. So when tau goes to minus infinity, that's the same thing as t goes to 0. And the picture I was drawing yesterday was that if you have the tau xi plane, and you have these 2 lines in the tau xi plane, then then in tx land, these lines become this forward parabola, and if I draw these lines out here, they become this forward parabola under the change of variables. So the only difference between this equation and the equation we were considering yesterday is this minus sign. But that minus sign makes a pretty big difference. Okay, so if we look for steady states of this equation, then those are self-similar solutions. So steady states capital U correspond to self-similar solutions, little u. So the difference that this minus sign creates is that yesterday there were no non-trivial steady states, and this time there are going to be a lot. Because what you want to do is you want to try to solve Navier-Stokes with self-similar initial data. So, so apologies, am I going to erase some of this stuff? No, I'm going to do this. So you want to solve Navier-Stokes with self-similar initial data. So you want U naught to be -1 homogeneous. That's the same thing as self-similar. So it should be like 1 over x. And now the initial condition turns into a boundary condition for the profile capital U. So if I'm trying to solve this steady state equation, just erase that detail. Right. So here's the steady state equation. And if I look at what the solution is doing at the initial time, so let's say I fix some x, and then I try to look at what's happening at the initial time. Because xi is x over root t, that's the same thing as looking at the large distance asymptotics of capital U. So fixing x and looking at what's going on at the initial time is like the same thing as looking at the large distance asymptotics. Say in these variables. Okay. So the correct boundary condition at infinity is actually, sorry, I have some limited space and I want to, so the correct boundary condition is that capital U of xi minus little u naught xi is big O of 1 over xi. Or little o, sorry. It's little o. Okay, so I want to discuss two mechanisms for non-uniqueness. One will be for the unforced problem, and one works well for the forced. I mean, they both work in either setting, really. But okay, let's talk about them. Two mechanisms for non-uniqueness. Okay, the first is a kind of bifurcation to multiple self-similar solutions. So the idea is you prescribe a single self-similar initial data, but you somehow have, say, 3 self-similar solutions. That's actually, this is what's going to be found numerically, and we'll look at some pictures, but that's kind of the idea. So this is bifurcation to multiple self-similar solutions with the same self-similar initial data, with the identical self-similar initial data U naught. And the other mechanism is going to be instability. But it's not just any instability. I mean, things are unstable all the time, and that doesn't mean that they're not unique. It's instability in the similarity variables. I think you can read it, but it's not the most pleasant. Okay, so let's talk about. So maybe I call these 1 and 2. So let's talk about 1. So when you talk about bifurcations, you want there to be a parameter. Our parameter is going to be the size of the self-similar initial data, or you can also think of it, I mean, it's also, you can consider it to be a Reynolds number. So here's how one goes. We're going to fix some, I'm going to call it A naught, which we want to be -1 homogeneous, in other words, self-similar, and divergence free. And let's say that its restriction to the boundary of the unit ball is smooth. It's self-similar, so if you know what it's doing on the unit ball, you know what it's doing everywhere. And we're going to take our initial data to be U naught is sigma times A naught. And it's actually not, it's not too difficult to construct this kind of data. You can use, for example, kind of shear flow, or not shear flows, kind of a these flows which are only in the E theta direction, and whose magnitude only depends on Z and R. So I mean, and you can cook up examples. So sigma is going to be our size parameter, which is also a proxy for the Reynolds number. And here's what we know. So when sigma is small, then there always exists a unique small self-similar solution of Navier-Stokes. There exists a unique small self-similar solution. I'll call it U sigma of Navier-Stokes. That's because when sigma is small, everything still falls into the standard perturbation theory, which people normally attribute to Kato, but many people worked on this kind of stuff. When sigma is small, everything's perturbative. The heat part of the equation is doing everything. The nonlinearity doesn't matter. What's not so trivial is that when you increase sigma, so as you increase sigma, there continues to be a self-similar solution of the Navier-Stokes equation. So there exists self-similar solution U sigma, whose profile I'll call capital U sigma. That's just what the solution is doing at time t equals 1. Remember that determines everything. So there exists a self-similar solution U sigma, whose profile is capital U sigma. And it has data U naught sigma, and we don't know whether it's unique. So as you increase sigma, you draw out a curve of solutions in the function space. So here's a function space capital X, here's sigma, I'll draw it a little bigger. All right, here's the function space X, here's sigma, and you're drawing this curve of solutions, capital U sigma. When sigma is 0, the solution is 0, because you're solving Navier-Stokes with 0 initial data. And then you have this curve. You can actually show that this curve is smooth. It's smooth at least until something happens. So you wonder whether there's another branch of solutions which is intersecting this curve. Maybe something like this pitchfork that occurs at some sigma critical, some critical Reynolds number. And if you have this kind of scenario, well, I mean that's called a pitchfork bifurcation or supercritical pitchfork bifurcation. And if you have this scenario, then you have, as soon as you're above sigma critical, you'll have 3 self-similar solutions all arising from the same self-similar initial data. And that's a kind of non-uniqueness. So why should you expect this kind of thing? So you might expect this kind of thing because it happens all the time for solutions of Navier-Stokes just steady solutions of Navier-Stokes. So you're just solving minus Laplace u plus, I mean, maybe we put Reynolds back in. Okay, 1 over Reynolds Laplace u plus u dot grad u plus grad p equals 0 with some boundary conditions with BCs. So within the class of steady Navier-Stokes solutions, where you forget about this extra term, remember, there's when you do the self-similar Navier-Stokes, there's this extra term that's like u plus c dot grad u. If you eliminate that term, and you just think about steady Navier-Stokes, these kind of bifurcations happen all the time. So what are we looking at here? Well, if you've seen my talk before, then you've seen the video version of this. But okay, let's just look at this still. What we're looking at here is two-dimensional flow past a cylinder. So you have some cylinder, and you have some cross flow, and you have some parameters that you can use to define a Reynolds number. For example, you have either the radius or the diameter of the cylinder, and you have the characteristic flow speed at infinity. That's a boundary condition. It's a boundary condition at infinity. And you also have whatever the viscosity viscosity of water, say. You can use those to define a Reynolds number. And you can also, by the way, you can also imagine that you're standing on some bridge and you're looking down at the supports and you're looking at what's happening on the surface of the water. That's not exactly what's happening here because that's actually a free boundary problem and there's stuff going on. But it's like this. So when the Reynolds number is very small, so in other words, just think the flow is very slow, then you're just going to see a solution of steady Navier-Stokes, which is laminar. And when you start to increase the Reynolds number, the flow is still laminar for some values of the Reynolds number, until you reach some critical Reynolds number, and then you'll stop seeing steady Navier-Stokes flow, and you instead see time periodic flow, which has this kind of vortex shedding. So you have this vortex pop off the top, pop off the bottom, pop off the top in an alternating fashion. And okay, of course, this is very old and very famous. And you increase the Reynolds number, the frequency increases, you can have further bifurcations. And this is kind of this is the picture. But when you increase the Reynolds number, past the critical Reynolds number, there's still a steady flow. I mean, you see the time periodic flow, because the time periodic flow is stable, but there's still a steady flow. You just don't see it, because it's unstable. But it's still there. There's still a solution of Navier-Stokes there. But, okay, there's no proof of that. But it's there. And it's numerically, people follow this branch of solutions very far. So this is a Hopf bifurcation. And anyway, this kind of thing just happens all the time in steady Navier-Stokes. We're looking at a problem which is basically an elliptic problem, just like steady Navier-Stokes. So a priori, there's no reason why you shouldn't have similar bifurcations. And so you kind of guess this. And then if you're John Sferak, you write down a meta-theorem. Okay, meta-theorem. I mean, they have an actual theorem where they cover a few scenarios. But here's the meta-theorem. Okay, if there's a bifurcation, I mean, when I write it down, it's going to seem very obvious. If there's a bifurcation, then there are multiple, okay, then there exists multiple suitable weak solutions with same initial data. So, okay, that's kind of obvious because, okay, if there's a bifurcation, there's more than one solution. So the scenarios that they cover in their paper are, they cover this saddle node scenario, also called fold bifurcation or turning point, and they also cover the Hopf bifurcation scenario. Okay, Hopf bifurcation, I mean, then it's more like then it's more like, at the sigma critical, then you have periodic orbits, which surround your unstable solution. So those are the examples they cover in their paper, but it's really just quite general. The solutions that they're talking about, these multiple self-similar solutions, they actually have infinite energy because the initial data is like 1 over x, and 1 over x is not in L2, so they have infinite energy. So the last part is that the bifurcated solutions can be truncated, so they have finite energy, and then you have non-unique Luray-Hopf solutions. They can be truncated to finite energy. Non-unique suitable Luray-Hopf. Okay, and then this is all conjectural until you put it on the computer. So this is Guillaume-Sferac. (2017). And you can also find these plots on Julien Guillaume's website. You could actually watch a video of what the solutions look like when you follow the curve. It's very nice. What are we looking at here? We are actually looking at the swirl part. Okay, we're looking at, here's R, here's Z. We're looking at the swirl part. So in other words, the E theta component of the velocity field of the similarity profile. And it's also, because it's singular, it's multiplied by xc. That's what's being plotted here. And we're seeing this pitchfork bifurcation. That was just the one that I drew on the other slide, like this. So here's sigma, here's x. This is the curve u sigma. And remember, you get to choose your initial data and look for the self-similar solutions. So they choose initial data, which has a reflection symmetry across z equals 0. And when you take sigma to be about 292, then you see this pitchfork bifurcation, which I see now is it's actually very small on the screen. It's big for me. You see a symmetry breaking. So this is one of the symmetric solutions. See, it's symmetric across z equals 0. This is one of the non-symmetric solutions. And then there will be one more, which is non-symmetric, but where this little swirl thing goes down. So that you'll have 3 self-similar solutions from the same self-similar initial data. So here's a plot of the low-lying eigenvalues of the linearized operator. And we can see, so when you have these bifurcations, you always need eigenvalues going unstable. So meaning that their real part crosses the imaginary axis. So here we're looking at sigma, this is the bifurcation parameter. Here's the real part of the eigenvalues. And here we have an eigenvalue whose real part, in their convention, goes negative, but there's a sign convention there. So in my convention, it goes positive. And that's where you have the pitchfork. Okay, questions about this? So let me just say something about the proof of this kind of meta theorem and the different scenarios that they consider in the paper. So when I say suppose there exists a bifurcation, there's actually just abstract kind of functional analysis that people have written down in books, and you just need to put the right functional setup on your self-similar solutions. Choose the right function spaces. And then you basically suppose that the conditions of that abstract theorem hold. So there are books about this. There's a book by Kielhofer called Introduction to Bifurcation Theory and Applications, or something like that. And okay, in the notes I have an example of one of the theorems called Crandall-Rabinowitz theorem, which handles these kind of pitchfork situations, but it's kind of just abstract. It's kind of just abstract. Okay. So let's talk about. This was all without force. I mean, it also works in the force setting. Let me talk about this second mechanism, which was instability in self-similarity variables. In self-similarity variables. So you have this, let's just say you have a single self-similar solution. Okay, suppose you have U, maybe UF is a self-similar solution. And the profile is capital U. So you take the equation I wrote U grad U, but I meant C dot grad U. So you take the Navier-Stokes equations in similarity variables. Okay, let's say equals PF, like this. And you linearize them around the self-similar solution. I'm actually going to call it U bar. Bar for background. When you linearize around something, it becomes a background, so we call it U bar. So the linearized equations, so you linearize, and you're going to have dtu. This term here, I mean, these three terms here, they're linear. So we just copy them. And then this term here, the nonlinear term, okay, becomes U bar dot grad U plus U dot grad U bar. All right. So these are the linearized equations. This linear operator here, I'm going to call it minus LSS applied to U. So I'm talking about instability and similarity variables. So what that means is that LSS should have an unstable eigenvalue. So if you put LSS in the right abstract framework, so I mean it has Laplacian in it, so it's an unbounded operator, closed and densely defined if you choose domain right, all these things. And what you'll find is that its essential spectrum must be contained to the left of the line minus 1/4, so there's a spectral gap. But you can also have some eigenvalues out here, and you could also have eigenvalues here, and in principle they could be accumulating on this line, but okay, I don't know. And okay, these eigenvalues out here, they're unstable because they're in the right half plane, and the linearized equation is dtu equals LSSU. So if there's a positive eigenvalue, you should see growth. And in this case, we say that the self-similar solution is unstable in similarity variables. So you can prove a theorem about this. And here's the theorem. Okay, suppose there exists a self-similar solution U bar, F bar. Let's say just that, let's just say that capital F bar is smooth and compactly supported. The profile of the force. Let's say it's smooth and compactly supported. That's what eventually we're going to apply this theorem, and the force is smooth and compactly supported, and it's fine. All right, suppose capital U bar is linearly unstable. And that means that this LSS has an eigenvalue with positive real part. Okay. Then, suitable weak solutions of Navier-Stokes belonging. So these ones, you have to be a little careful. They're not automatically going to have finite energy, but they're belonging to the class U bar plus continuous in time, 0 to t with values in L2. Okay, intersect L2, H1 are not unique. So this is some combination of ideas that are in Gian and Sverak and also the ABC paper. And if we can just verify this, if we can find that capital U bar, which is linearly unstable, then this theorem says we're done. So tomorrow we'll talk more about how do you find capital U bar. But today I just want to focus on this part. If you had instability in self-similarity variables, how would that give you non-uniqueness? What does that mean? Okay, actually, throwing back to Gianluca's talk, in that case, to find these solutions of force Navier-Stokes that have anomalous dissipation, you get to choose the vector field and then define the force a posteriori. I just choose my U. I say it solves Navier-Stokes with some force, and the force is the right-hand side when you plug in. We're also going to use this, this trick. And maybe that seems like cheating, but the thing is, even if you let yourself have that flexibility, it's really non-trivial. So eventually we're going to pick our U bar. It's going to generate some force, but we need to pick it in the right way so that it's linearly unstable. And it's not going to be so easy. All right. For the previous scenario, we kind of saw what the non-uniqueness looked like. It was like there are these multiple self-similar solutions, or maybe there's some hot bifurcation, time periodicity. I need to tell you what the self-similar solutions look like in this case. And for that, we're just going to talk about ODEs. Okay, so I just want to talk about ODEs, and I'm just going to even restrict to a simple class of ODEs. ODEs for which the nonlinearity is bilinear. Okay, ODEs. So more generally, all right, you can look at x dot equals f of x near some equilibrium, and you can linearize around some equilibrium, and you'll get an ODE like this, but the nonlinearity is not going to be bilinear. Let's just take this bilinear one, because that's what Navier-Stokes is bilinear. All right. So now, the solution that in this case, we're interested in the stability of the solution 0. Okay, so stability of x equals 0. Because you've already centered your problem around x equals 0 by, say, linearizing. And now we're interested in the spectrum of the linearized operator. Okay, so let's say the spectrum, L is the linearized operator. So the spectrum of L, let's say it looks something like this. So spectrum of L, it's an ODE, so I don't know, it just looks like something. It can have some central stuff. Maybe it has a 0 eigenvalue. I don't know. But it has these unstable eigenvalues. Now, if you have some eta, okay, before I say that, associated to these unstable eigenvalues is a spectral subspace, meaning, I mean, directed at graduate students, meaning, okay, you just write L, which is a matrix, in Jordan form, and then, okay, the subspaces associated to those eigenvalues, those are the spectral sub. That's, if you project onto that subspace, we call it spectral projection onto these eigenvalues. And if you start with some, so let me call that subspace EU. This is kind of standard notation. Unstable subspace. It is eigenvectors and generalized eigenvectors associated to those eigenvalues. And let's say you start with some eta in EU. Okay, then you start solving the equation d tau eta equals, you start solving the equation, let's say, I'm going to call it d tau x ln equals L x ln, and maybe x at tau equals 0 is equal to eta. So what's going to happen to this solution of the linearized problem? Well, it's associated to some unstable eigenvalues. So forward in time, it's going to grow exponentially. But backward in time, it's going to decay exponentially because it's unstable forward in time, but it's stable backward in time. So this is just the linear picture. But there's a way to turn this linear picture into the nonlinear picture. And there's a construction associated with that. And that construction is called, I don't know, construction of the unstable manifold. Unstable manifold is the nonlinear counterpart solving that nonlinear equation of this picture. So what it basically is it's a manifold of solutions to the ODE, which backward in time converge to the equilibrium exponentially, and which track the linear dynamics to the leading order. They track the linear dynamics. So, I mean, let's even have a theorem. Okay, theorem. I mean, if you just look in books on dynamical systems, you find the proof. All right, unstable manifold theorem. So suppose that the spectrum looks like what it did on the previous slide, and so let's call this real part on this line, okay, real part of lambda equals m. The line going through the least unstable eigenvectors. So suppose that gamma is less than m. Okay, then there exists an injective analytic map which maps the unstable subspace to, it maps small data in the unstable subspace to solutions in this class C gamma, not the Holder class. So by the way, what is this C gamma? I mean, C gamma, I really mean by the C gamma class, I really mean solutions which, I really mean functions which decay backward in time at the rate gamma. So this map, it maps sufficiently small data. It maps small data, A naught, okay, in the unstable subspace to solutions of the ODE, satisfying this. The unstable part at time 0 is equal to A naught. This lets you, so PU is the projection onto the unstable subspace. So this comes with an estimate. So the estimate is that the solutions X, their C gamma norm, is controlled by, let me just write it like this. So pointwise, these solutions decay backward in time, like e to the tau gamma, a naught tau less than 0. So they decay backward in time exponentially to the equilibrium, which is 0. Okay. So you can say more than this, by the way. Any solution which backward in time decays to equilibrium exponentially must be one of these solutions. So all the solutions that decay backward in time with some rate, exponential rate, belong to the image of this map, at least after you time translate them. And the solutions track the linear dynamics. They track the linear dynamics in this sense. So let me just say, let me define kind of a generalized subspace in the sense that if I draw some line here, real lambda equals gamma prime, and I define EU gamma prime to be the unstable subspace corresponding to eigenvalues to the right of that line with real part equals gamma prime. So you draw some line, real part gamma prime, and you just look at the subspace associated to stuff to the right of that line. Okay, then so if A naught is in e to the u gamma prime, then you further have this minus e to the tau L A naught less than 2 gamma prime tau A naught. This linear part here, e to the tau L A naught, backward in time, that's bounded below by e to the tau gamma prime. This is the leading order behavior. If you subtract it off, the solutions decay, the remainder decays even faster. So that's what I mean by this tracks the linear dynamics. This is just, just perturbation theory. Okay, questions about this? I'm going to connect it to Navier-Stokes, and then we'll have lunch. It'll be nice. It doesn't. This doesn't have. I'm talking about the whole manifold. Yeah. It doesn't have to be the most unstable eigenvalue. Just. Yeah. Okay. I guess in this picture I drew it as the most unstable, but okay. I don't know. Let's just say there's 2 more here. Yep. Yeah. So this is just some ODE stuff. Okay. This works for PDEs. This works for semi-linear parabolic PDEs really well. And the proof is like the ODE proof, but okay, there's an additional aspect, and sometimes you need to use that the operator smooths you a little bit. But okay, it's semi-linear. So, there's a classic reference for PDEs, which is a book by Henry. And unfortunately, the typesetting is, it's really typewriter. I had the idea of maybe I should get some people together and we're going to retype this book. It's classic. But I don't want to do that. I don't want to spend time on that. So Henry does this for semi-linear parabolic PDEs. It's not difficult. It's difficult to do everything really cleanly and really nice, but it's not difficult. All right. So let's say that we have this in the Navier-Stokes picture. So I have basically what that theorem told us is suppose LSS has an unstable eigenvalue. We could have many. Then there are solutions U which look like U bar plus some leading part. So e to the tau L eta or A naught or whatever you want to call it. Maybe I'll call it A naught. I'll call it eta. So this is this linear part plus a remainder. So let's just say that this is associated to eigenvalue A. And let's say that it's an eigenvector. So the remainder will be big O of e to the 2 tau A. So you have these solutions. Okay, so you have these solutions. Here's tau equals 0. And here, this is the equilibrium capital U bar. And they converge backward in time exponentially. So this is like e to the tau A. So remember, they track the linear dynamics, and the linear dynamics tell you there's some instability. So backward in time, it looks stable, and it converges to the equilibrium. And now remember, you're making the ansatz u equals 1 over root t, capital U, xi tau. And so in the standard picture, here we have tau going to minus infinity. In the standard picture, this simply becomes t equals 0. Okay, t equals 1. Because remember, tau's log t. And in the standard picture, here, it's not u bar, it's really little u bar. And this looks like it's separating with some polynomial rate. So for example, L infinity. So your solution u minus u bar, L infinity is going to be like t to the minus 1/2 plus a, something like that. In L3, it's going to be like u minus u bar. Sorry, it's not. It's actually it's like this. The L3 norm is going to be like t to the a. Because I'm using that e to the tau a is t to the a. And the norm, okay, there's some dependence in the norm because there's this 1 over root t factor. But in other words, what you're finding is you're finding solutions which separate from the self-similar solution at a polynomial rate. And at time t equals to 0, they're exactly equal to the self-similar solution. So this unstable manifold picture, it's just about instability. And normally the instability process takes infinite time. That's what's going on in this picture. It takes infinite time. But because you're in similarity variables, when you pass to physical variables, the process takes finite time. And basically, the way to think of it is this: the solution lives on many length scales. There's a self-similar solution. It basically lives at length scale root t. And let's say you make some perturbation of this self-similar solution. The time it takes for the perturbation to double is related to the length scale that the solution is at by some power. So, I mean, let's just say, for the sake of argument, the time it takes for the perturbation to double is equal to the length scale that you're currently at. So if you're at very small scales, the perturbations double very quickly. And what you get is you get some kind of geometric series which says you can make infinitesimally small perturbation, which doubles and doubles and doubles and doubles, on a sequence of times corresponding to a summable geometric series. And so the thing can go from size 0 to size 1 in time 1. So that's the picture here. Okay, we're omitting many details. Tomorrow we'll talk about how do you choose this capital U bar. And we're going to talk about some basic hydrodynamic stability stuff. So those of you who aren't in London at the Hydrodynamic Stability Conference will get some of it here. And it'll be good. All right, thanks.
Are there questions?
Just a curiosity about the flow past the cylinder.
Yeah.
What is known at the rigorous level? For instance, linear instability is known?
Not known.
It's not known?
Yeah.
Okay. Thank you.
experimentally known.
Also numerically, I guess.
And numerically. Mathematically, I don't know, super open. As open as Geospheric. Yeah.
Other questions? Okay, so we thank again the speaker. Okay, so welcome back for this afternoon session. The first speaker is Paolo Bonicatto, and since they told me it's not, well, here it's tradition not to say the titles, okay, so I just let him speak.
All right, so good afternoon, and thank you very much for the introduction, and thank you very much for having me here. I'm very pleased to take part in this event, within this frame of the Riemann Prize Week. So today I would like to tell you something about some recent investigations that I've been carrying out together with Philip Rinder, my postdoc supervisor at Warwick, and Giacomo Del Nin, who recently left and is now in Max Planck Institute in Leipzig. So the main topic will be currents, Euclidean currents, and possible evolutionary models for currents. But so I will be basically, the topic is a combination of partial differential equations, a bit of geometric measure theory, with some flavor of calculus of variations, if you will. But before properly kicking off, let me give you a quick outline of my talk. So I start, of course, with an introduction, where I will try to tell you what problem we want to study and where it comes from. And then I have a sort of intermediate section where I'll be brushing up a bit the theory of currents. So this section will be mostly notational for most of you, but I'll recalling the basic ingredients of the theory of currents, and relying on these, I'll be able to write down an equation which we call the geometric transport equation, which is the one of the main characters of this talk. And then in the third and last section of the presentation, I'll tell you about our findings. And in particular, I want to discuss with you an existence and uniqueness result. And I'll try to present a few glimpses from the proof that we have. And then I'll conclude with some few words on an example, basically, on these Rademacher type results. But particularly, I want to present an example which is somewhat exotic in a sense, and I thought it was fitting within the framework of this conference. All right, so without further ado, let me start, and let me start with an introduction. So I don't really want, with this audience, to motivate the need for the study of transport type equations. I'll just limit myself to the following basic consideration: that transport phenomena are pretty much ubiquitous in nature. They appear constantly in physics, in engineering. And let me say that common mathematical framework in which you can cast, in which you can study these transport phenomena, is usually provided by two partial differential equations, which are very well known and very and well studied. So we have, on the one hand, the continuity equation, which I'll be writing in this way, and on the other hand, the transport equation, the advection equation. And in both models, the letter B represents a fixed given velocity field. And let me say the continuity equation particularly will play a role also later stages of this talk. And here is written in terms of a density, rho, but of course you can also write it for measures. And it really, let me just say very quickly that it has, I mean, its physical meaning, it's well known. So this is the equation, for instance, satisfied by the continuous density of the density of a continuous distribution of particles that are moving according to the velocity field B. Now, turns out, for a variety of reasons that I'll be explaining, and I hope you will agree with me in 10-15 minutes, but it turns out that basically the continuity equation is well suited to say, it describes, can be used to describe the motion of zero-dimensional objects, in a sense. And at the same time, this formulation, the transport equation, describes the advection, the motion of top-dimensional objects. So I'll try to convince you of this claim. But if you believe me, as of now, you see that there's a rather compelling question that that emerges from here, right? So you have a way of writing down an equation for the transport of zero-dimensional object. You have a way of writing down an equation for top-dimensional object. What happens in between? Okay. So basically, what we want to, where we started is, can we write down some transport equation where the quantity that is transported, that is advected, is a, say, generically k-dimensional, possibly rough object? Now, of course, one has to properly understand to give some boundaries to the study. And, well, one way of defining, of making rigorous this notion of k-dimensional, possibly rough set goes via the theory of currents, okay? And as promised, let me now recall a few bits of the theory of Euclidean currents, particularly those bits that are necessary for me to write down an equation that will somehow bridge between these two equations. So let me try to be precise. I'll fix an integer, which is d, which is the ambient, the dimension of the ambient space, and k is another integer between 0 and d. Now, what's the definition of a current? So, strictly speaking, I mean, in rigorous terms, a current, a k current, is defined as a linear and continuous functional on the space of compactly supported smooth differential k forms. Now, one cheap way that I quite like to keep in mind while working with currents is you can see currents as the vector valued analog or multi-vector valued analog to distributions, okay? So I like saying this because in as much as generalized distributions, if you want, currents provide us with the right framework to study a variety of problems under, say, weak regularity assumptions, okay? And just as from a notational point of view, well, omega will always be denoted a form by omega usually, and T, the capital T, is the letter that I've chosen to denote currents. Now, yeah, this is the rigorous definition. Let me give you some easy example that you might want to keep in mind for the duration of this talk. And actually, it's really not, there's no loss of generality as far as this talk is concerned. If you think of currents as vector valued or multi-vector valued measures, okay? So you have already, all of you basically have seen this object. So if you want an example of a one current, just imagine a vector value, what is usually called vector valued measure. So a vector field, a given vector field tau and a scalar measure, then the object tau mu defines one current. And this carries over to the higher dimensional setting. So if you want an example of a k current, well, it's, if you want, a k vector field multiplied times a scalar measure, all right? So, of course, if you, let me say, special classes of currents arise if this vector field and the measure mu have some additional structure. And this is what gives rise to the wide classification of currents. You have integer rectifiable currents, integral currents. And these special subclasses of currents won't play a major role in this talk, but they will pop up again towards the end when I'll be discussing this example. But keep in mind, if you, I mean, I don't want to really dig into the definition of these classes. Let's say that if you, so what is an integral current, a one integral current in RD? Well, it's just a collection, a superposition of Lipschitz-oriented loops, okay? So it's really, you see from here that there's a way of understanding k-dimensional objects as currents, okay? And let me say that for the first part of the talk, the class of currents I want to work within is the class of normal currents, which is a relatively large class of currents. And those are defined as the currents that are of the form tau mu, whose boundary is still representable in the same form, is still a vector valued measure. Now, what is the boundary of a current? Well, in general, the abstract definition of boundary is written here on the slide, is simply the adjoint to the exterior differential. Okay, so you're given a k current, you construct a k minus 1 current, so some functional that will act on k minus 1 test forms, and you prescribe. I mean, this is the definition that you give. Okay, you're basically, if you have in mind this geometric picture, you are enforcing the validity of Stokes' theorem essentially, but I mean, this is a fairly general definition, and let me stress, the normal currents are those currents for which that are vector valued measures, and the boundary defined this way is still a vector valued measure. All right? Okay, I need one more ingredient from the theory of currents, if you want, which is the differential operator, which is the Lie derivative operator. So what I want to do is I want to construct an operator that measures how a current changes in, say, a given direction, along the flow of some velocity field, so to speak. And this is not completely surprising, I believe, because we do have such an object when we speak about forms, right? So when we study, say, differential geometry, we study the Lie derivative of forms, precisely defined in such a way that it measures how the forms changes along the flow of the vector field. And, well, what can we do for currents? Well, out of duality, essentially, we can write down a definition, which is the one on the slide, the boxed one. And I have to confess that I don't really like this definition, because it's a bit maybe abstract, and one does not really see from here why this is the right definition. And let me say, though, that this is this is a definition that makes sense whenever you have a velocity, a vector field B, which is defined, say, everywhere, but you don't need any particular regularity on it in order to give such a definition. And let me try to justify, let me try to convey the intuition behind this formula, how it comes about. Well, yeah, first let me just say that, of course, this is defined, you have this wedge product appearing in the formula, that it's not really important. It's the generalization, if you want, of the multiplication operator when you're working with distributions. But let me try to say why this is the right formula. Well, this can be obtained if you recall the so-called Cartan's magic formula for the Lie derivative of forms. So usually when you study differential geometry, you are given some formula for the Lie derivative of a form, and then in differential geometry books, it's proven as a theorem that I have to confess I've not been able to trace back whether it was Elie or Henri Cartan, so one of the two, established this remarkable formula that allows you to express this Lie derivative in terms of the differential operator and the contraction operator alone. Now, if you dualize this formula, passing from forms to currents, you end up with a formula that is written in the red box, okay? And this is, say, this duality trick is what is behind this definition. All right, I think that I have now all the ingredients to sort of close this gap, to bridge between these two equations that I promised you at the beginning, because the equation that you can write for k currents is the geometric transport equation that I've written down on the slide. So you have now, you are looking, if you want, for a curve of normal k currents, and you prescribe that the time derivative of this path, of this curve, equals up to a sign to the Lie derivative in the direction of the velocity field B. Okay? And if you want, you can also prescribe an initial datum as is written on the slide. And let me say that, of course, there is consistency in this scheme, in this picture, because if you write down the geometric transport equation in the case of zero currents or for top dimensional currents, you end up precisely with the continuity equation and the transport equation. This is very easily, for zero currents, as I told you, zero currents are essentially distributions, or actually if you restrict to currents of finite mass, they are measures. And so you end up with the continuity equation in the class of measures. Okay. Now, we have written down this equation. One fairly natural question that one might rise right now regards the well-posedness of this equation. Can I establish some well-posedness result for the geometric transport equation? The answer is yes, and this is the first result that I want to discuss with you today. This well-posedness result is obtained within the class of Lipschitz vector fields. And let me give you the statement, and then let me discuss a bit some ingredients of the proof. So we are given a bounded and Lipschitz vector field defined on Rd, and we fix an initial datum, normal k current, and then we claim that there exists one and only one solution to the geometric transport equation. This solution is unique in the class of normal k currents, and we have I would say an expected representation formula for the solution in terms of the push forward operator. Okay, so I'm not rigorously defining what the push forward operator is, but let me just say x subscript t is the one parameter flow generated by B, which is well defined because B is Lipschitz. And well, what is the gist behind this formula? So the intuitive idea is that really what I'm doing is transporting, advecting the initial current along the characteristic lines of the field, right? So this is the first result that I want to discuss with you. And let me first of all, let me say that the existence bit of this theorem is not hard. Is relatively easy, and you can easily establish existence if you want by means of approximations, and it's, I mean, the problem is linear as usual, so this is not the hard part. What is a priori what could be a bit trickier, say, is the uniqueness. And the uniqueness might be, I mean, this is sort of heuristic comment, so let me try to convince you about the let me tell you where the difficulties related to the uniqueness lie. So you see, if you have a velocity field which is Lipschitz, so is its flow, right, by standard results. But now what happens is that a priori the currents, the initial datum or the transport currents, might stay exactly in the set which is not so good for the Lipschitz flow, right? So Lipschitz maps are kind of okay if you look at them under, say, the Lebesgue measure. But if you work with, say, normal currents, well, you might end up in a situation where your currents live in points where the flow is not fully differentiable. And this is somewhat the problem, because this prevents you from performing pointwise computations, which is what you would like to do when you try to establish uniqueness. Let me try to dig a bit more in this direction, and let me. So I would like to offer some more comments on this part of the proof. And what I actually want to do is to give you almost a complete proof in the case k equals 0. So I don't want to sort of engage with the burden coming from the notations with differential forms. So I'll restrict my attention to the case k equals 0, so measures. So the duality is just with the functions. And I want to give you the uniqueness proof in the case k equals 0. And let me recall you once again that in this, under this additional assumption, the geometric transport equation is nothing but the continuity equation. Okay, the continuity equation in the class of signed measures. Okay, so, and let me add that this statement, so when k is equal to 0, the existence and uniqueness of the solutions to the continuity equation in this framework is very well known. And I refer you, for instance, to the book by Ambrosio Gigli Savaret if you want to see an alternative argument. Okay, but this is well known. And let me offer you an alternative proof, which contains the ingredients that we'll be using for the higher dimensional case. Okay. First, let me sort of discuss, let me specify in which sense we understand this equation. This is, of course, understood in the sense of distributions. So I prescribe that for any smooth test function, this integration by parts formula holds true. Okay, this is the usual way of understanding this equation in the sense of distribution, and the measure mu t is here. Okay. So what do we want to show? We want to show uniqueness. Okay, having prescribed an initial datum, but actually let me prove at once the uniqueness and also the representation formula. Okay, so I claim that if I'm given a solution to this equation, then the solution is necessarily this form, is the push forward, is the transport of the initial measure along the characteristic lines of P. Okay, so this is the claim. Let me just some cosmetic tricks. So let me rewrite this equality in the following way. So this is equivalent to saying xt minus 1 push forward mu t is mu bar, which by means of the semigroup law becomes x minus t push forward mu t is mu bar, which, using the fact that the flow map at time 0 is simply the identity, is actually equivalent to saying this map as a measure valued map is constant. Okay, so my goal is the map t to sigma t is a constant map. Okay, right. Let me sort of restrict now. Let me show you a very easy argument when the velocity field is smooth. Okay, so a lot of I mean, this is maybe a bit vague, but let me just say that usually in these transport problems, everything or almost everything when it comes to uniqueness pivots around the choice of a right test function. Okay, and well, if you have a smooth velocity field, you want to use as test function, you want to pick this test function phi. So phi is a test function in time and space, of course, and it's written as a product of a smooth function of time, alpha of t, times beta, so a smooth function of the space variable, but beta composed with the inverse of the flow. So sort of cylindrical test function, if you want, so these functions that follow somehow the flow of the vector field. And let me justify why I'm claiming that this is the right test function. Well, just let me remind you, you have to, so when you pick the test function, you have to compute this integrand, right? You have to compute the time derivative of the test function and the directional derivative of the test function in the direction of the field. All right, so let us compute this integrand for the specific test function that I have chosen. Okay, so this is a very simple computation that you can do. So if you compute the time derivative and the directional derivative, you realize that some cancellations happen, of course, because of the specific choice of the test function. Because when you evaluate the directional derivative, you will see that you will be getting by chain rule some terms involving the directional derivative of the flow in the direction v, in the direction of the velocity field. So there are some cancellations, and you end up with this fairly simple formula. So the integrand will just be alpha prime of t times beta of x minus t. All right, so you plug this in, and you know, so phi is a smooth test function, so you plug it in. This is 0 by definition because mu t is a solution. But you have just computed this is alpha prime times beta. And now what do we do? Well, let's just rewrite this with using push forward notation for measures. So this is the measure x minus t sharp mu t acting on beta, everything multiplied times alpha prime, integrated in time. And now if you look at what we have here, we are saying, since alpha is arbitrary, it's an arbitrary test function of time, well, we are saying that the derivative in the sense of distribution of this map, right, t maps to sigma t applied onto beta, is 0, which means that the map is constant, and actually playing with the arbitrariness of beta, you get really that the map t to sigma t is a measure valued map is constant. Okay, so this is exactly what you wanted, right? We wanted to show that sigma t is constant. This was our claim, and we have achieved, we've proven it, if the vector field is smooth. Now, what happens when the velocity field is merely Lipschitz? Let's think for a moment. So, if the vector field is only Lipschitz, which is the case we care about, well, what happens is that the let me just, apologies for this. Let me just go back. Yeah, observe the form, the specific form of the test. If the vector field is Lipschitz, as I told you before, so is its flow. So a priori, this function phi will be merely Lipschitz in space. And now it's not completely clear that you are allowed to use this as a test function, right? Because, recall, you have to differentiate the function phi, and okay, in the direction b, but you have to integrate with respect to mu t. And so what happens? It happens that since there is no, let me go back to this slide. So the test function phi is now only Lipschitz, as I said, so it's not clear whether it is admissible or not, right? Because you don't have Rademacher result, or you don't have Rademacher theorem for general assigned measures, so you're not sure that the integral makes sense mu t almost everywhere. Now, in the particular case of the continuity equation, there's an easy way out. If you want, you can easily work by approximation and sort of show that that specific phi is admissible indeed by means of an easy approximation argument. But let me use another. Let me give you another argument that hinges upon a refined tool which has been recently brought up by Alberti and Marchese, and it's a fundamental tool by now fundamental tool in geometric measure theory. And this is the notion of decomposability bundle of a measure. So let me, before introducing you to the decomposability bundle and telling you how I intend to exploit it, let me offer you a possible reformulation of the continuity equation that it will come at hand and will be very helpful in a moment. And I'll be using again currents, if you want, in order to reformulate the equation. So it is very well known that the continuity equation, written in this way with the measure mu t, can be equivalently stated by saying that a certain current in the space-time is boundaryless. So if you see, I'm defining, so this S is what? Is a vector valued measure. I mean, it's the fact that I'm working in the reason why I have this 1b L1 tensor mu t is just because I'm working in the space-time, okay? So I have just one coordinate more. But it's an object of the form vector times a measure. So this is one current, an object of the form tau mu, where tau is some field in the space-time and mu is a measure in the space-time. And you can easily check that if you, prescribing that the boundary of this current is 0 is equivalent to this equation. So in particular, the current S will be normal. If you have a solution, the current will be S will be boundaryless. So in particular, it's normal. And when you have a normal current, you can rely on this result by Alberti and Marchese that asserts the following. So given the current S of this form, 1b times this product type measure, what happens is that the vector field 1b belongs to the decomposability bundle of the associated measure L1 times mu t at almost every point Tx in the space-time. Now, of course, you would be asking me, okay, but what is this decomposability bundle? What's the definition? You see, I've not given any definition. And actually, I don't really want to give you the rigorous definition. Let me just say, I just rewritten here. So this is the same statement as in the slide before. Essentially, by definition, this means that you have that every Lipschitz function on the space-time is differentiable in this direction, 1b, at almost every point with respect to this measure L1 times mu t. So essentially, the decomposability bundle is the set of directions of admissible directions, of the differentiability directions of every Lipschitz function. So my personal understanding of this deep and profound result by Alberti and Marchese is the following. So when it comes to differentiability of Lipschitz functions, we all know, we all think immediately to Rademacher theorem, and that's fine. But okay, there are also other versions, and say maybe more geometric in some sense, because if you're given a Lipschitz function and you're given a C1 manifold, well, you can't say that the Lipschitz function is differentiable almost everywhere on the surface. That's, of course, that's not true. But you can say that the Lipschitz function is tangentially differentiable almost everywhere with respect to the surface measure. And my personal understanding in this result by Alberti Marchesi is a far-reaching generalization of this from C1 manifolds to normal currents. Okay, so to potentially much objects that are much weirder than a C1 manifold. But what is the, how do we exploit this decomposability bundle? Well, we exploit this decomposability bundle at the fact that 1B belongs to the decomposability bundle because we can conclude that every Lipschitz function is admissible in the continuity equation. It's admissible and it satisfies the right integration by parts formula. Okay, so we really use, there's Alberti Marchesi came with fairly explicit formulas for the directional derivative if you want, and so you can conclude that you can use your function phi as before with basically the same result. So the having a solution to the continuity equation implies that this integration by parts formula holds true for every Lipschitz function on the space-time. Okay, even if you have just mu t. And yeah, let me sort of underline and stress the fact that the reason why we can apply Alberti and Marchesi result is because we only care of the derivative in the direction 1b of the test function, right? So this is precisely what we are looking at when in the integrand we are precisely looking at the directional derivative of phi in direction 1b. And thanks to Alberti and Marchesi, we can say that this exists mu t almost everywhere, and it will be 0 whenever integrated. So basically, this allows us to conclude the proof in the Lipschitz case for the continuity equation, because the same argument that I presented to you before carries over to this Lipschitz setting, because we are sure that we can use that function, and so in particular we obtain that the measure valued map t to sigma t is constant, which was equivalent to the uniqueness. Okay, so essentially it's the same proof that you can perform in the smooth case. It's just fine even if the vector field is only Lipschitz. And yeah, let me say that this was the proof in the case k equals 0, or at least some ideas from the proof, for general k greater than 0. So when you work with currents, with k currents, the strategy is somewhat similar, not completely identical, and we still rely crucially on the decomposability bundle and on the formulas that follow from the result by Alberti and Marchesi. Okay, so this concludes essentially the presentation of the first result, this well-Posner's result. And let me add a few more words on this example that will conclude my presentation. And in order to do that, I would like to start by offering, if you want, an alternative point of view on this business around this geometric transport equation that we've been discussing so far. So the alternative point of view is the following one. Let's start again from the continuity equation. It is very well known that the continuity equation is strictly related and actually characterizes absolutely continuous curves of measures. And this is true remarkably in the Euclidean space, of course, but also in much wider generality, also in the non-Euclidean setting. And I didn't want to state precisely any theorem as of now, because I think we have already seen enough. But I mean, let me refer once again to the monography by Ambrosio Gigli e Savaret if you want to see a precise statement. But basically, you have that. If you have an absolutely continuous path of probability measures with finite p momentum, and absolutely continuous is understood with respect, say, to the Wasserstein distance, then you can construct a velocity field that transports these measures. Okay, and well, quite naively, one can ask at this point, okay, is there anything similar available for k currents as well, for k strictly greater than 0? So if I am given some Lipschitz or absolutely continuous path of currents, can I find some notion, some geometric derivative which is transporting these currents? Now this question is maybe a bit too vague, as I've stated it here on this slide. So let me maybe ask a more specific question. And I like presenting this question in the following way. So now I'm sort of restricting my attention to integral currents. But imagine for a moment in your mind, imagine a pipe, a cylinder, right? And in my interpretation, the time direction goes vertically upwards. And you're given this cylinder. Okay, so a rectifiable surface, cylindrical pipe. And suppose that if you slice this cylinder with horizontal planes, okay, you have these slices of the currents, and suppose you have some Lipschitz control on the slices of this current. Okay, so I'm basically selecting a fairly particular Lipschitz path of currents, which is the path arising from the slicing of a k+1 current. So, but we postulate, we assume that these slices are Lipschitz in time. And, well, I'm not discussing really the metric structure that I'm doing the space of currents with. We suppose that this Lipschitz behavior is with respect to the flat distance, strictly speaking to the integral flat distance, which is a right generalization of the Wasserstein distance. So the sort of conjecture that one can come up with is, okay, if I have a Lipschitz path of currents, I might expect, I would like to say, maybe I'm witnessing a transport phenomenon. I mean, maybe what I'm looking at are just a bunch of curves or loops that are transported by a velocity field. And I would like to construct this velocity field explicitly in terms of the tangent, in terms of the vector field that describes the approximate tangent space to the cylinder. And so the question is, this question whether you are witnessing or not a transport phenomenon has in general a negative answer. And this was, to us it came somehow as a surprise, because we were expecting that having Lipschitz behavior in time was sort of ruling out the possibility of flat regions, right, of horizontal regions. And so we sort of thought, okay, yes, that should be okay. We should be able to write down a vector field driving these slices. And, well, in general, the answer is no, it's negative. And we have identified actually the necessary and sufficient condition for this to be true. And this is what we call the negligible criticality condition. So this is the formal statement, if you want. So given the pipe as above, this k+1 integral current, there exists this geometric derivative, this velocity field driving the evolutions of the slices, if and only if you have this control on the set of critical points. What are critical points? Critical points are exactly what you may be thinking right now. So critical points are the crit S is the set of points where the tangent space to the pipe is horizontal. Okay, and if you have that the current does not charge this set, you have a vector field driving the evolution, and conversely, if you have a vector field driving the evolution, you don't charge the critical set. The point is, this property, you will see in a moment, is not necessarily satisfied by Lipschitz in time integral currents. And let me say, this is sort of, this is a, if you want, a Sartre type property, Sartre type definition in disguise. So you can show actually that this negligible criticality condition is equivalent to the following, to saying that the projection onto the time axis of the measure restricted to the critical set is orthogonal to L1, and this is kind of reminiscent of a Sartre type property for currents. But the point really, what I insist, and I'll be showing you now the example, is that this condition is not necessarily true under the assumption that, under the sole assumption that the path is Lipschitz, because what happens is that when k is greater than 0, strictly greater than 0, it might happen that the path of currents that you have as sort of Lipschitz or regular in time, but as criticality, as singularities, if you want, that are spread out in space. And let me conclude with really now the sort of exotic example, which we call the flat mountain. And yeah, I guess that some of you in the audience, particularly the chairman, might recognize the initial inspiration that we took from for constructing this example. And let me try to describe a bit more what we did. So what you see here on the slide is just a few steps in the construction of what? Of two integral currents in the space-time R times R2. Okay? And so if you iterate this procedure, what you end up with is you end up with the graph of a BV function defined in the unit square. And this is indeed an integral current, and it has the following property. If you slice this graph, right, so with horizontal planes, with t constant, and you measure the flat distance between, say, the slice at time t and the slice at time s, well, that's truly Lipschitz, actually linear. I mean, the flat distance between the two is proportional to t minus s. So this path of currents, if you look at it from the time perspective, it's completely regular. It's Lipschitz. But the point is that in the limit, this surface, this two-dimensional graph, has everywhere tangent space which is horizontal. So in other words, the negligible criticality condition is violated here in a pretty severe way, in the sense that almost every point in the unit square will be critical, because the tangent plane will be horizontal. And so you cannot, I mean, what this example conveys is that you're not witnessing any transport phenomena here. I mean, this evolution cannot possibly be driven by a velocity field. Okay? And this is an illustration of the fact that indeed there's a sort of decoupling, if you want, of the regularity in time and the criticality, the singularity in space, which is something that you cannot observe when you are looking only at measures, so when k is equal to 0. And yes, with this exotic example, I'll conclude my presentation, and I want to thank you all very much.
Are there questions?
So you talked about, I mean, this is all in the setting of Lipschitz velocity fields. So do you have, for general K currents?
Yeah, the previous part, yeah.
Do you have any feeling of what would be, because I mean, for continuity equation, transport equation, of course, there is like Sobolev, BV, you know?
Yeah, for the transport in particular.
So is there anything, because here you rely fundamentally on the fact that the flow is Lipschitz.
Okay.
So, I mean, is there any hope to extend this?
That's a very good question. I mean, I'd like to work on this for many years. So my impression is that there should be a way of defining this in a weak regularity, under weak regularity assumptions on the velocity field. I don't think that we have the machinery as of now ready, because you see, when you study the transport equation, you rely heavily on the well-posedness at the regular Lagrangian flow level, right? You use that notion. And now my impression is that the notion is very well suited to those kind of problems, but you see, when you are transporting currents, the regularity of the flow kicks in. The regularity is a map of the initial datum, if you want, because you see, I'm defining the push forward of the initial datum. In order to do that, as you were pointing out, I'm relying on the fact that the flow is Lipschitz. And to me, it seems that the regular Lagrangian flow, I mean, perhaps is not the right notion to use, because it's very, it behaves rather poorly from this point of view. It's not regular in any way. From this point of view. So, yeah, I hope. I mean, I really would like to dig in this direction, but as of now, I'm not able to tell you anything rigorous.
Okay. Other questions? Okay. So, thanks, Paolo.
Thank you very much.
So the second speaker of this afternoon is Punshon-Smith, and okay, you can
Okay. So thanks for the introduction. It's great to be here. I know it's warm in here, and I know it's just after lunch. So if you fall asleep, I don't blame you. Actually, it's a little easy right now. I'll try to keep it somewhat interesting and exciting, and maybe I won't put too many proofs in here. So I'm going to talk about advection diffusion equation. In the context of stochastic velocities, some of the things I'll talk about will be maybe put in a lot of generality, and I'll try to explain maybe a general program. And you know, some of the things here, and particularly, chaos and mixing, are works that are now pretty well established, as well as some new stuff that I'm going to talk about as well, norm equivalence, and I'll say what that means in a second. So we're going to consider the advection diffusion equation, and in particular, I'm going to consider a general form that also has a source term. So here, G will be our mean zero passive scalar. We'll just be working on the torus. And I'm only going to be working on the Lipschitz setting. So we're going to have velocity fields that are Lipschitz. In fact, they're going to be much more regular than that. They'll be essentially smooth. And U is divergence-free. And what I'd really like to be considering is something that, U solves some fluid equation like the Navier-Stokes equations, or, could be any host of other equations. But from a physical perspective, I'd like to consider something that you actually see physically in nature. And this source term here is actually something that could be somewhat physical. Is that if you were modeling something like the spread of temperature fluctuations or pollutants in the air or water, as is at least roughly modeled by this equation, then generally there's some source that's inputting scalar or maybe taking it out from the equation as well. And this kind of thing typically settles this equation to some equilibrium or some balance where the amount that you're putting in is sort of eaten up by what's dissipating. And in particular, despite the equation being linear, the long-time behavior can be extremely complicated. And you see here, this is kind of a typical steady state of this equation, where you end up with lots of sort of Swiss roll patterns and self-similar scales, a lot of different things going on here. And generally, if I let this thing go long enough, if the velocity field is suitably rich in its motion, this kind of pattern will just sort of dance around forever. All right, and part of the question is, well, how are the scales in this picture distributing themselves? So this kind of picture is referred to as passive scalar turbulence, or at least in the smooth velocity setting. So despite the velocity being very regular, the picture can be somewhat rough. And in fact, the smoother the velocity field in equilibrium, the rougher the picture gets. So let's talk just a little bit about the decaying problem, because if I get rid of the source, what happens in the decaying problem actually tells you a lot about what happens to the problem with source. And in this case, it's very well known, very easy to prove that the scalar decay is exponentially fast in L2. But in particular, I want to know what its optimal rate is. So I'm going to say, let's take the logarithm of this thing. Let's take its maximal value over all initial data in L2, and then take the asymptotic exponential rate and call this thing lambda L2 kappa. A priori, generally, you don't know much about what it is. Here, we know that it's at least negative, but it could be minus infinity. Okay, minus infinity meaning that typical scalar actually decays faster than exponentially. I'll talk a little bit more about that in a second. But if we do the really naive first-year graduate, or I don't even know, undergraduate energy estimates on the heat equation, it's very easy to see that this thing is negative, and in fact, bounded below very easily by the diffusion constant. All right, so this is just heat equation estimate. But we'd like to get a little bit better information. So how exactly does this rate depend on kappa? Is sort of one of the main motivating questions. Of course, I flipped the subscripts here. Hopefully that doesn't confuse you too much. And the second question is, in fact, how does this constant, how does it actually depend on the space that I'm measuring these things in? So if I were to instead use a typical estimate, you can consider much more complicated spaces, but if I measure it in H1 or H-1, which, H1 you expect to have some kind of growth, at least temporarily if there's gradients forming in the equation, in h-1 if there's a lot of mixing happening in the equation. So how do these rates actually depend on the space? And then finally, how quickly are these rates actually achieved? Okay, so and we'll see in a bit. Since I'll be working in a stochastic setting, these rates, while they exist, they may take, 1 million years before you finally see them, or something like that. So some of the questions are: can we get some idea on exactly how long you actually have to wait before you see these? So first, let's talk about mixing. So for no diffusion, for the kappa equals 0 problem, there's many equivalent ways to define mixing, and there's many different ways that you may want to quantify it or measure it. One of them here would be if I take the h-1 norm, which I'm going to define just by duality with the h1 norm. And I sort of wrote it this way actually to make a point, because in fact, if kappa equals 0, we know that the solution gt is just a push forward under the Lagrangian flow for the velocity field. And if I just use the fact that it's volume preserving and change variables, I can throw it onto the f and I get f composed with the flow times g. And that quantity in dynamics is known as the 2-time correlation function. And in fact, its exponential decay is something that's very well studied in dynamics. Exponential correlation decay is something that's deeply related to uniform hyperbolicity, and in other cases non-uniform hyperbolicity in dynamics. Okay, but in fact here from a PDE setting, it's really just the h-1 norm. So if we start with data that's somewhat regular, then the h-1 norm decays exponentially fast, so we say it's exponentially mixing. And in fact, mixing, in terms of h-1 decay is really due to the formation of small scales sort of globally in the picture. So generally, you take something which is really smooth, and then you flow it into the map, and it gets all twisted and tangled up and forms really small, thin filaments everywhere. And these filaments forming sort of everywhere in the picture will make the h-1 norm decay. Now, I'm not going to go too much into mixing. Actually, there's a lot of works, and a huge number of works, as we know, on mixing for advection diffusion equations. Just to name a few in sort of the rough velocity setting, Yayo and Gelatos had some initial work actually showing how long it can take for velocity fields in Sobolev spaces to actually mix, and then also how they can unmix. Tarek and Gelatos actually constructed Sobolev regular velocity fields that, using ideas from dynamics, they constructed sort of a time-discrete Baker's map thing that they made continuous in time, and showed that these things are actually exponentially mixing. And then, there are sort of related works sort of showing that you can construct not just rough velocity fields that mix in finite time, but velocity fields that are Lipschitz that actually are also exponentially mixing. But all three of these examples are examples where they're explicitly constructing velocity fields to do something very specific. I should mention the very recent work by Tarek, Kyle, and Jonathan on, it's another Lipschitz setting where the velocity fields are sort of alternating wedge flows, so shear flows that have a little point at the edge. And it's just a time periodic flow, and they were able to show that this thing is also exponentially mixing. And in fact, they show something a little bit stronger, which I'll talk about in a second. But of course, there's a lot of works in this area, and it'd be pretty much impossible to cover them all. But the one point I want to make is that it's an extremely difficult problem. If I hand you a velocity field and I say, tell me if it's mixing, it's going to be really hard. In fact, you will likely fail, except in very special cases. But mixing has a very special effect on the advection diffusion equation, as many of you know. If I have mixing, it causes often what's known as enhanced dissipation, or there's sort of an enhanced decay of the L2 norm. So in particular, high frequencies get generated exponentially fast, and then they get fed into Laplacian, and so the equation decays much faster than this naive heat equation bound that we had before. So stated in terms of these decay rates, this lambda kappa L2 that I defined before is actually, much, much more negative than kappa, right? Especially for kappa small. But sort of phrased more precisely as this typically written, you look at the first, the time it takes to lose half of your L2 mass, and you see that time scale is much smaller than the same time scale you would expect for the heat equation. And there's been a number of works actually sort of studying exactly how and when you get enhanced dissipation, particularly how it comes up from mixing. So one of the first works was by Konstantin Kiselev, Rizhik, and Zlatos, where they essentially showed that if you have some kind of mixing behavior, that you can show that this is actually enhanced dissipation. And they even gave some sort of spectral theory-like condition about having no H1 eigenfunctions for the advection operator that gives them some enhanced dissipation-like property. In fact, there was a work by Michele Cote-Zelati, Mattias Delgadino, and Tarek Al-Gindi, where they actually show that if you take a mixing velocity field, that it just directly implies enhanced dissipation. You just don't need to know anything about the velocity other than it's mixing. But in their case, they show essentially that the time it takes for you to mix to the scale is on the order of log kappa squared. Now, it may not be immediately obvious, but that is actually not the same as what's known to be the optimal rate. So it's known that at least in sort of the Lipschitz setting, you can't really mix faster than log kappa in terms of the scaling. And there's a number of heuristic arguments for why that's the case, but at least at this point there was no clear examples for, there's no clear condition for if I give you a mixing flow, is it actually going to be enhanced dissipating at an optimal rate? But in fact, it is possible. So this is again very recent work. Tarek, Kyle, and Jonathan proved in their wedge flow example that not only do they mix, but they mix uniformly in the diffusivity. And if you mix uniformly in diffusivity, you get an optimal enhanced dissipation rate. And I'll talk maybe a little bit more about how you see that in a second. Okay, so one of the things that you're actually fighting typically when you have diffusion here and you have mixing is that there's really no known exponential lower bounds on the decay of the equation. So if you take the advection diffusion equation, this lambda kappa could very well be minus infinity. I mean, I think it's not generically, but there's no proof of that. It's pretty much an open question for such a simple equation. The best known lower bound is in fact double exponential. So that intuitively speaking, if you knew the equation were somehow localizing in frequency and it sent Fourier modes to Fourier modes, then mixing means that Fourier mode is growing exponentially fast, and then the Laplacian is decaying like e to the frequency times t. So the thing will double exponentially decay if you were somehow able to do that. And in fact, if you work in discrete time, there are plenty of examples. So if I instead alternate diffusion with some hyperbolic toral automorphism and repeat over and over again, this model is known by, Gautemeyer and his PhD student showed that this example, in fact, decays double exponentially fast. And in fact, if you work in the class of hyperbolic toral automorphisms of the torus, it's in fact generic. So most of them do that, and only a few don't do it. But if you instead sort of work within the continuous time setting with Lipschitz velocity fields, there's a whole host of numerical observations done by Doring and Miles, where they show that you don't see it. So pretty much everything is decaying exponentially fast. Yep.
In the case of autonomous vector field, it is known whether lambda k is known.
Not even, no.
Doesn't it look like a spectral problem?
You'd think so, right? So the spectral theory, you might get some discrete spectrum, but it could all, let's say I use spectral. It could all be accumulating. If you do it on a compact operator, all the spectrum could be at zero, kind of thing. So even then, you don't know. So currently, there's no known example.
These ones are example of double exponential. The cat map is double exponential.
The cat map's double exponential, at least in this sort of pulsed diffusion setting. Yeah.
Okay. Is there a transport version of this, vector for that, like the one of the?
No, I don't think it's clear. No. Yeah. The Baker's map one, I'm pretty sure the Baker's map. Well, okay. Actually, that one, there is some, after talking to Jean-Luc Defoe, I think they have some numerics that show if you take the Baker's map, split evenly down the middle, and you do a pulse diffusion, that it also double exponentially decays. But if you slightly shift the skew point, or the point where you're folding and cutting, it becomes just exponential again. So the Baker's map is sort of in the setting where generically it's not double exponentially decaying, and only very special configurations double exponentially decay.
So there is no rigorous result?
No, that's numerical. I don't know any proof of it. Okay, so that, if anyone can find one example of initial data in one velocity field that's not zero, that has an exponential lower bound, let me know. But okay, so I want to work in the setting of stochastic velocity fields because, in fact, if the velocity field is stochastic, things become much more tractable. You can use dynamical systems or random dynamical systems. You can use ergodic theory. You can kind of say it's very low probability that certain bad things happen. And so there's a whole set of really powerful tools from the theory of random dynamical systems, ergodic theory, and particularly spectral theory for Markov semigroups that we can really strongly utilize. And in fact, the primary example I want to consider is going to be the stochastic Navier-Stokes equations with some Whiten time forcing, suitably smooth in space, but non-degenerate. So meaning that every single Fourier mode is turned on, so that if you know what it means, the semigroup for this equation is Strong-Feller, so that it's regularizing as an infinite dimensional equation. But I don't want to get too much into those technical details. In fact, if you like, you can also consider three-dimensional equations, hyperviscous stochastic Navier-Stokes, at least enough so that the equation is well posed. Stokes equations in 2D or 3D, or any finite dimensional fluid. And in fact, if you don't really know much about stochastic fluid mechanics, just think about this example. Take a velocity field, which is the sum of shears in different directions and different phases, and just modulate them by independent Ornstein-Uhlenbeck processes. If you do that, this example will satisfy everything I'm talking about. Okay. And another example, and I'll bring this up in a second, in fact, is what's known as the Pierre-Humbert flow, which is a random series of shear flows where, in fact, you just move the phase of the shear randomly every time you apply it. And so this one has actually been studied recently by Alex Blumenthal, who's one of my collaborators, and Michele Cotti-Zalati and Gavalani. Galvalani. Sorry, I don't know how to say. This is Italian. Okay, so let me mention a couple theorems we proved. I'm not going to talk much about the proof of these because these are maybe sort of old news, maybe. So let's take U to be one of the velocity fields that we had above. Then there exists some rate gamma. Sorry, let's just call it gamma. Ignore the star there, which is positive. And it doesn't depend on initial data, and it's deterministic, such that for all initial data in HS, where S is big enough, it doesn't matter. Then there's some random constant where you get exponential decay. And no, this estimate's almost sure. So it's what typically in random dynamics you call a quenched estimate. So here we're saying there's no averaging going on. It's almost surely true. And it's important to note the velocity field, the random constant it depends on the initial velocity field, but does not depend on the initial data. Okay, so it only depends on the initial data linearly through the right-hand side. Okay, and not only that, but this thing has good moments, and in fact, you can give it better moments if you like. All right, but let me just give you a general principle. If you want to know whether a certain random velocity field that's suitably smooth is exponentially mixing, generally speaking, if the velocity field is sufficiently non-degenerate, in the sense that as a stochastic process, it's exploring enough of all the possible velocity fields, then the scalar will almost surely mix. Okay, so almost sure mixing is kind of a generic phenomenon. All right, it's hard to say it exactly in the sense of genericity, but in the sense of non-degeneracy here, that's what it fits into. And the same proof techniques for this theorem have been used in this recent work that I mentioned by Alex, Michele, and I think postdoc maybe, and as well as some other recent work by Benjamin Guess and Yaro Sletstev, where in this case they actually study stochastic transport equations, so that they kind of extend the work to the case where you have Whiten time velocity fields.
Sorry, just
Yep.
a question. So this is for every time, right?
This is for every time.
So definitely.
And for T to infinity, of course, yeah.
My question is, if you want an estimate only for 2 to infinity, you improve on the constant. I don't know.
Sorry, perhaps I repeat. No, my question was like if you want only an asymptotic estimate, do you improve on the dependence of the cons, or does something improve, or you expect? No?
I don't know of any way to do that. Yeah, I mean, some of what I'll mention is a little bit about studying only the time asymptotic setting through studying infinite dimensional Lyapunov exponents. But then you get random constants that in fact are even harder to estimate than these ones.
Okay.
So there may be a way, but not any obvious way that I know. Yeah.
But so you would not expect that like you have this mixing, but in reality asymptotically is a bit better. I don't know.
Yeah, I mean, yeah. As you're suggesting, this D is sort of telling you some information about how long it takes till you see exponential decay, right? Like here it's telling you if you weight timescales log D over gamma, then you see, then finally you see exponential decay. Yeah, I don't know of any way. Okay. I'm going to give you an extremely rough idea of the ingredients in the proof. I think maybe to the point where it won't make any sense, but ask questions if it doesn't. So we're using techniques from random dynamics. So really it's a Lagrangian approach. Okay, so we study the flow associated to the velocity field. And in fact, because everything's really smooth, we can use we can use the theory of Lyapunov exponents. So in this case, we study the asymptotic sort of stretching of just the flow map, and it's known. I think in the examples I was giving you before, if you stack a bunch of hyperbolic toral automorphisms, these are uniformly hyperbolic maps. So they have a clear stretching direction and they have a clear compressing direction. These kinds of examples in dynamics are also quite easy to show are mixing. But in this case, especially if we only work in 2 dimensions, you're not going to have flows that have that for most of the time. And in fact, if you look at the 2D stochastic Navier-Stokes equations, it's full of vortices everywhere, which don't have that picture locally. And so, we have to really look time asymptotic and say that, okay, well, maybe I can show that at any given moment in time I don't see it, but if I look long enough in time that I do get positivity. And this theory has been pretty well developed, and particularly in the random setting, there's a very rich theory sort of in following from some initial works by Harry Furstenberg in the 80s, where essentially you can either think of it group theoretically or Lie algebraically, but this is kind of the non-degeneracy condition I was mentioning before. If you have your velocity field that's being driven as a stochastic process, if you look at its gradient, so it's a strain matrix, if you look at this as a matrix, and you look at the Lie algebra generated, and I'm being kind of vague here, but over all the possible modes that you can reach, so all possible configurations that the Navier-Stokes equation might reach, or if we just consider this case, just take these 4 modes. Okay, if you look at the Lie algebra generated by this, if it's SLN or all traceless matrices, then in fact you should have a positive Lyapunov exponent. Now, I'm really greatly oversimplifying it, but heuristically that's the idea. It's a rigidity theorem. So if you have essentially the only way you can have a 0 Lyapunov exponent is if the group or the Lie algebra generated by this thing is degenerate and doesn't fill up all of SLN. Okay, so this is how you get a positive Lyapunov exponent very loosely. But in fact, to go from a positive Lyapunov exponent to mixing requires some work, and in fact, it requires some work using Markov semigroups. So the main idea is that mixing is actually implied if you study instead the Markov semigroup for 2-point Lagrangian motion. So that is take any two particles in the velocity field that don't start at the same point and let them move around. If you can show that motion is geometrically ergodic or converges exponentially fast to its stationary measure as a Markov process, of course, these are not actually Markov. You have to also include the velocity field itself for it to be Markov. But roughly speaking, if it's Markov, then in fact you'll have mixing, And really the idea is that if you can show something converges exponentially fast to its stationary measure, it's equivalent to showing that this operator has a spectral gap, at least for positive time. And that spectral gap is key. So somehow the spectral gap is exactly giving you the thing that's generating the mixing. Okay. Now I'm not going to talk too much about how you actually show the spectral gap. It's pretty complicated, but it uses machinery from the theory of Markov semigroups and the Harris theorem. But generally speaking, there's a nice little trick to go from decay of this thing, which is some sort of an averaged thing, to something which is almost sure or quenched. Because what you can do is there's a nice little Borel-Cantelli trick, where you can roughly say that that you have some decay almost surely if you have suitably fast exponential decay of the two-point motion. And I'm not going to talk about it too much, but this trick was actually, I think, first introduced by Dolgopiat, Korolov, and Koloshin in 2004. At least that's where we first learned it. But I think, in the Sinai school, it's been known a lot longer than that. Okay, so that's mixing. Right, but I mentioned that you can also get mixing that's uniform in diffusivity, and this is the real power of the stochastic methods, because it allows us to not just say, okay, we have mixing, but the mixing, we can slightly quantify exactly how the mixing is happening with respect to the diffusivity. So, in addition to the picture I mentioned before, if we work in the exact same setting, the velocity field solves stochastic Navier-Stokes, and you have some initial data that's in HS and all that. You get the same exponential decay estimate. Of course, the equation is decaying as well, but you have a rate now that does not depend on kappa. Okay, this rate, gamma, is uniform in kappa. The constant can depend on kappa, loosely speaking, but its moments are uniform in kappa. Okay, and so this is what I call uniform. This is what we call uniform diffusivity mixing. And I'll just mention, I mean, it's not an easy result to prove, because, and this is the reason in general combining diffusivity with mixing is such a hard problem, is that adding on a Laplacian in kappa, so let's say this is the generator, so to speak, some differential operator associated with the two-point semigroup. When kappa equals 0, this is the thing I know has a spectral gap, and then I put this perturbation on it. You should know that if you try to perturb operators with a high-order perturbation, in fact, this is the highest-order derivative, or at least a high-order derivative in the equation, then the spectrum doesn't always behave very well under high-order perturbations. However, what we show, and what generally you may expect to be true, is that the spectral gap is continuous in the perturbation. Okay, the rest of the spectrum can be doing all sorts of terrible things when you perturb it like this, but the spectral gap behaves nicely, and because of that, you get essentially an estimate like this. Again, very loosely speaking. All right, and because of that, in fact, if I know that I have h-1 decay, it's an easy sort of interpolation argument to say, well, if I can actually show that the L2 norm decays also uniformly in kappa, but you have a constant out front which now clearly diverges as kappa goes to 0. Okay, but if you look at this and you say, okay, let's ignore the kappa dependence on D for a second. This tells you here that I have exactly a log kappa time scale for when I see. So if I weight log kappa time, then this whole factor will be decayed by roughly a factor of 1/2. Okay, or order 1. Okay, and so what this tells me is that the L2 rate that I defined before is bounded uniformly away from 0 by this rate. Okay, so this means that not only is it not bounded away from, it is bounded away from kappa being 0, but in fact, as you send kappa to 0, it stays away from 0. Okay, so there's some kind of anomalous, so quote unquote, decay of the equation.
The estimate of d kappa doesn't depend on kappa, the expected value.
This exactly. This does not depend on kappa.
What are the assumptions on U, or where's U?
It's let's say the same assumptions as in this one. So let it solve stochastic Navier-Stokes or any one of the models we had before. And again, to warn, the stochastic Navier-Stokes case should have non-degenerate noise forcing it. Okay. So, and let me just mention one more thing, since we're maybe talking about constructing exotic solutions or something like this. If you now go back and take these solutions that we constructed and you add a source term back to it, so that the G equation now settles into an equilibrium. If you look at the process, which is the velocity field and G as a couple, this is now a Markov process in some infinite dimensional space. You can show it has a unique stationary measure pretty easily. In fact, with almost no conditions on the noise, you just need the B to be non-zero. And mainly that's because the Laplacian here is contracting, so everything is getting, and the G equation is getting squeezed into a point. Because of that, you have this unique stationary measure, at least for each positive kappa. If you have uniform and kappa mixing, it actually implies tightness of these measures in all negative Sobolev spaces. That's more or less what this type of estimate's giving you, a uniform H-1 estimate. And because of the way negative Sobolev spaces embed into each other, you get tightness in these spaces. And so in fact, up to some subsequence, there's a limiting measure that lives on H- that solves the inviscid problem. Okay, so what this does, it allows you to construct a infinite statistically stationary solution to the inviscid or the advection problem with a source. And that's non-trivial because the source should make, you're constantly pumping scalar into the equation and it has nowhere to go. Of course, the point is that in negative Sobolev spaces, it does have somewhere to go. It mixes away. Okay, so getting uniform and kappa estimates allow you to construct these kinds of, they're all distribution valued. In fact, you can show that for any LP, the mu0 gives 0 mass to LP functions. So in fact, they're just truly distributional things that are dancing around. Okay, but if it's right now, another open problem is if this measure is unique, it's not clear. There are maybe some strategies you could use to prove it, but right now, it would be very nice to know if you could construct a unique limiting stationary solution for this. Okay, so let me talk about some of the new stuff that I was hinting at maybe. So I had the second question I asked was how do these rates depend on the norm in the space I'm using? So let X be one of the following, H1, L2, H-1. Of course, you could pick a lot of other spaces. So if I denote by lambda x kappa the asymptotic rate with respect to that norm, this question was actually more or less studied by Doring and Miles for very specially constructed flows. And here they have this lovely picture where exactly you're looking at the log of the particular norm on the vertical axis and just regular time in the x-axis. And what you see is, of course, each of these curves here is kappa. Sorry, this is large kappa, and then kappa getting smaller is going up. So as you take kappa to 0, you get closer and closer to these sort of asymptotic curves. And if kappa were not here, the H-1 norm would decay, the L2 norm would be preserved, and the H1 norm would grow. But the second you add diffusion to the problem, the scalar will typically follow that curve for a while, and then it will kind of deviate and saturate at some exponential rate. Same thing for the L2 norm and same thing for the H1 norm. So it has a little transient period where it does something else, and then eventually it starts to see exponential decay. And what you should see from the picture is that the rates are all the same, more or less. So the slopes, you see the same slope, whether it's H-1, L2, or H1. But let's make this a little bit more precise because we have a velocity field which is ergodic. I need to use a tool that is, in fact, the key engine behind what I'm about to present. So there's a very, at least in dynamics, there's a very well-known theorem known as the multiplicative ergodic theorem, or short, the MET. And the way I want to think about this is as follows. So let me think about the solution to the decaying problem. I have some solution operator, ST, which sends the initial data to the solution at time t. And I'm going to view it as an infinite dimensional random dynamical system. So this U dependence here, this boldface U, is going to be the entire history of the velocity field. So in a sense, the solution at time t depends on everything the velocity field was doing from time t to time 0. And what we also know is that the time t evolution, at least when t is positive, is a compact operator for if you have diffusion, because things are regularizing. And moreover, you know, if we're working with stochastic Navier-Stokes, I don't want to get into too many of the details there, but this, I'm going to assume that sort of the map that sends t to, sends a velocity field to a point later in time is ergodic with respect to some probability measure on path space. Now, for the stochastic Navier-Stokes equations, for many other sort of ergodic fluid models, this can be done. You can just, if you know you have a stationary measure, you can just build a measure on path space that's invariant under shifts. It's kind of what it means to be stationary. But you know, so that's what we have. And under a pretty mild moment assumption, the multiplicative ergodic theorem in infinite dimensions, so this is due to Ruel, says that actually these limits that I was writing before, they don't have to be lim sups. They exist. So if I take any initial data, there exists some lambda x kappa, which is actually this limit. And this limit exists for every single initial data in whatever space I'm working in. And in fact, they're not random. So they only depend, in this case, on the initial data. And in fact, they only depend on where the initial data is pointing. That you can clearly rescale the initial data and you get the same number. But there's actually much more you can say about them. So in fact, these numbers, as they depend on the initial data, they only depend on sort of a discrete set of values. So this thing, in fact, only takes a set of numbers which we know are at least always finite. And there's some, let's say, you can think of like a frequency cutoff where there's some series of numbers that go down. These are known as the Lyapunov exponents, the largest one, and then they keep arranging smaller and smaller down to some value that I just cut off at. And there's a so-called filtration of finite codimension spaces. So specifically, I mean, these are infinite dimensional spaces. And in fact, this one is equal to x, but they all nest inside of each other. And they're sort of not properly, they're properly contained inside of each other. And so if I look at the space fi minus fi plus 1, in fact, sorry, if I look at the orthogonal complement, and not ignore what I wrote there, but they're finite codimensions. So they sit inside of each other, but there's only finite dimensional space that lives sort of between the two of them.
So is the sequence ordered by
It can be infinite. So this lambda c, I can pick. It's basically for every lambda c, which is finite. It's a slightly technical statement of the assumption, but you can actually. So maybe I should have really written lambda c can be minus infinity. But you can also have a sequence of finite Lyapunov exponents, and then the rest are just equal to minus infinity, or in fact they can all be equal to minus infinity. Sort of, and that's the kind of picture that's going on. All right, so this lambda k takes these values if you happen to be in one of the spaces but not the next one, not the one under it. So if you're in this one, everything sort of gets attracted to the lambda I value and so on. So as you see, this means that if you're in f2, or sorry, if you're in f1 minus f2, you only see the lambda 1 as the limiting value. Okay, is that clear? I know maybe many of you have not seen this theorem, but we actually will be using it a lot. So the main theorem, in fact, that we prove is the following. Now, the theorem is actually much more general than this, but I'm writing it sort of in this particular context. The theorem can actually be stated for sort of general compact linear evolution equations in arbitrary Banach spaces. But here, if we work in the setting of the advection diffusion equation, if we assume that the velocity field is ergodic and satisfies a very simple moment assumption, so if we just assume that the average of sort of the time one integral of this thing is finite for Sobolev parameters bigger than, so anything that embeds into Lipschitz, or where Lipschitz embeds into it, then, it embeds into Lipschitz, then actually none of the Lyapunov exponents depend on the space you're measuring it in, at least up to the spaces where the equation can actually be well defined. Okay, so this means that they don't depend on HS, at least for S between minus gamma and gamma, where gamma is the regularity of the velocity field. All right, and in particular, if I take F for some larger space and restrict it to the smaller space, then you get the smaller F. Okay. So just to write it in the picture that we were looking at before, the H1, the L2, and the H-1 lambdas are all the same. Okay. But I should mention this theorem can also be applied to many other things. You can apply it to the magnetic dynamo equation, which is sort of vector advection problems. You can apply it to linearized Navier-Stokes systems. And you can also work in Banach spaces, not just Hilbert spaces. And okay, maybe I have a little time. Until 3:50 or something? Up to 4. Okay. So, right. So that's the statement. I'll talk a little bit about the proof at the end. The proof, the very general proof is technical. The proof for the top one is not so bad, actually. But let me give you one more sort of statement, and this is sort of answering a little bit of what Maria was asking. Is there's a corollary of the MET that says that, okay, well, if I have any of these Lyapunov exponents, lambda 1, let's say, in fact, this statement is even true if they're equal to minus infinity, then the rate, then the whatever norm you're measuring, so pretend this is L2 or something, can be bounded above and below by exponential rates for any fixed epsilon, which is positive. So, you know, I can bound it below by something which is a little bit worse than the Lyapunov exponent, and bound it above by something which is a little bit better, or a little bit stronger. And there are two constants that show up. There's this d underbar and there's a d upper bar, which if you know a little bit of the theory of Lyapunov exponents, these are known as Lyapunov regularity functions. And they are almost surely finite. Okay? And in fact, also, sorry, I should mention, we have this other factor here, right? And this is just encoding the fact that if you, sorry, that should be F2, I apologize. That as long as you're not in F2, then you get this exponential rate. If you're in F2, then you get lambda 2, and so on as your lower bound. So, and in fact, you can be quantitative about it. So this is measuring the angle between the initial data you took, and that, again, that should be F2. All right. Now, if I pick the d, which is actually the biggest of these two constants here, then if I just pick an initial data that either perfectly or lies roughly orthogonal to the space, again, sorry, that's a typo. It should be F2. Then just the statement of the MET that I wrote before, if I just subtract lambda 1 minus this and use these statements, in fact, we see that we get a slightly better quantitative estimate on how 1 over t log g is actually approaching lambda. And in fact, it's directly related to log of these Lyapunov regularity functions plus epsilon, over t plus epsilon. And so this is telling you exactly, it's saying that this is the time scale. Okay, so if I weight time roughly order epsilon to minus 1 log of this constant, then 1 over t log g is epsilon close to the top Lyapunov exponent. All right, so getting estimates on this give you estimates on how long you have to wait, which in the picture I'm showing was the sort of how long that slope lasted for. Okay. And I should mention one more thing. I mean, these estimates say that if I know that the top Lyapunov exponent, or in fact any of the, let's just say the top Lyapunov exponent is not minus infinity, then this tells me I have an exponential lower bound. Okay. At least away from some positive codimension set. And that would mean that if you find it for one initial data, it actually implies it immediately on a much, much larger set. So if you prove it for one initial data, it immediately becomes true sort of generically. So on a set that's just very big minus a finite dimensional piece. All right? And in fact, the previous estimate that I mentioned says that I don't care what norm you measure it in. So if you can find exponential lower bounds in pretty much any norm, then you'll get L2 exponential lower bounds away from a positive codimension set. Sorry, when I say positive, I mean positive and finite, too. Okay. So now, how do I estimate these guys? So, I mean, in fact, for the stochastic Navier-Stokes equations example we had before, this is what Maria was kind of suggesting. I know I can estimate the h minus 1 d constant, at least the upper one. And I know I have just finite moments on it. All right. But if I switch between spaces, the d's change. Okay, they don't necessarily have to take the same amount of time. So the h minus 1, it may take longer. I mean, in the picture that Dorian and Miles were showing, they look to be roughly the same, but I think a priori that doesn't have to be the case. So you may, if I measure something in a really strange, let's say, Besov space, it may take longer for you to finally see the exponential growth. Whereas if I measure something in some really precisely constructed anisotropic Sobolev space, then maybe I see it immediately. And so what we also show is that, well, if you compare these Lyapunov regularity functions between Sobolev spaces, you can actually get an estimate on the ratio of the two. So if I compare, let's say S2 is the larger space. If I compare D for HS1 to D for HS2, for technical reasons we have to pick slightly different epsilons here. Then in fact the constants that you get, that compare so the ratio of the two, have logarithmic moments with, I mean, okay, there's some technical constraint on how big the moments can be, but the important point is that these logarithmic moments scale like log kappa. And that means that you actually, you don't ruin the optimal enhanced dissipation time. Okay, so if you get enhanced dissipation in one, you get enhanced dissipation in all. At least at worst, you get enhanced dissipation in all with the optimal scaling. Okay, this one is perhaps a little bit technical to prove, but I think in the remaining time, I'm going to talk a little bit about how to prove the equivalence. So the fact that all the norms are the same, at least for the top Lyapunov exponent. Okay, so let me mention one thing. So if I pick S2 to be bigger than S1, trivially, I can bound the bigger space by the smaller space, right? And so if I take the log on both sides and 1 over t, this tells me trivially that at least I have this direction. Okay, that's easy. The hard direction is to go the other way, right? Because we know that in general, I can't really bound. I can't flip this inequality for Sobolev spaces. However, to go the other direction, what we do is take F to be this F2 space. So the space that if you're in it, you usually see the lambda 2 growth, but if you're outside of it, you see lambda 1 growth. And what we do is we pick something that's in the orthogonal complement of this. Now, in the Banach space setting, this is more complicated because there's not a clear orthogonal complement, but you can pick a transversal that's sort of measurable selection kind of thing. In this case, this turns out to be measurably varying. And let me project, so note that this space is finite dimensional because they were positive finite codimension. And let me project onto that space. Okay, so it's finite dimensional. And in fact, because the multiplicative ergodic theorem is an ergodic theorem, this space is invariant in this sense. So if I evolve this finite dimensional space forward under the dynamics, it stays finite dimensional. And it only evolves just by shifting the velocity field under the ergodic evolution. Okay, and what I do is we project out all the higher dimensional stuff. So if we just project onto this finite dimensional space, project the initial data and project the output, it turns out that this turns out to be also well-defined what's known as a cocycle, which is the kind of thing that you can apply the multiplicative ergodic theorem to. First off, as sort of by construction, the way it's built is that for this finite dimensional thing, we actually see these same rates if we measure in HS2 and HS1. Okay, that's maybe, I don't quite have enough time to explain exactly how to show this, but it's not terribly hard. And I mean, they're really, because these spaces are constructed to be projecting always orthogonal to this F2 space, then we always see the top growth. That's sort of how they're cooked up, right? And so because they give us the same Lyapunov exponents, what we need to do is try to flip that inequality that I wrote before. So originally we had this, and I want to go the other way. Well, to do that, let me pick a subspace which is finite dimensional. All right. So if I pick something which is called the Grassmannian of the bigger space, that's a finite dimensional subspace, then this alpha is exactly the constant that measures the reverse inequality. Okay. But note that constant will blow up as you take E more and more infinite dimensional. right? Because we know that all norms are equivalent on finite dimensional spaces. So this thing is sort of measuring how big the deviation is. Okay, and so what we can do is, well, there we go. We can flip. If I put this constant in here, I can flip to the larger dimensional space, and I use the fact that this thing is living on this space EU. Okay, and because it's invariant here, everything is bounded by alpha of EU of just some shift of the velocity field. Okay, and so now if I take log of both sides and 1 over t and send t to infinity, we split it into two terms. As the log turns into a sum. This one is going to be lambda hs1, and I have this other piece, which is I need to show goes to 0. All right, and the problem would be that, well, I don't exactly know how to control this. Okay, but in fact, it's not so bad, and this is because of ergodicity. So if you don't know enough ergodic theory, it's okay. I'll maybe try to give you an intuition for it, but essentially, because this map is an ergodic map, it means that, there's a sort of recurrence theorem, the Birkhoff recurrence theorem, which allows me to say that, well, okay, there's some good set where this alpha of E is less than some fixed constant, and I can just pick a sequence of times where I'm just going to keep returning to that set. So if I just follow that sequence of times, this alpha will be bounded by a constant. And because of that, it drops out, and you get the equivalence. Okay, the higher dimensions, yeah. So that's the proof for the top exponents. The rest, getting the equivalence of the rest of them is a lot more technical, but I think that this idea is at least somewhat simple. And I think yeah, that's everything.
Are there questions?
Which norms can you take as X? Like, can you take something badly anisotropic? Positive derivatives, negative derivatives, I don't know.
So the way we defined it, so the theorem is more general. It says, if I have some linear evolution equation which is well posed on two different Banach spaces, and one is densely embedded in the other, densely and continuously embedded in the other, then under some extremely mild moment assumption, which is essentially that the velocity field, like if you're trying to prove well-posedness in whatever space, maybe you do some commutator estimate to show that that you can actually get well-posedness, and that not only that, but let's say the log of the time one evolution map, or sorry, the log of the ST. Let's say this guy, if we know that this has good moments at one time, then it's true. So I think for badly anisotropic spaces should be okay. I mean, as long as they're Banach, and I think they don't even really have to be Banach. Yeah, it gets a little hairy. I mean, the MET, the most general version of the MET we can apply is for Banach spaces, and the cocycles don't have to be compact; they can be quasi-compact. And but yeah, I think that's as general as I know how to do it.
Other questions?
Question. No, a very philosophical question, a bit from outside. Like. In all these, your vector fields are pretty smooth, and you assume well-posedness. I mean, why is it so important? Why can't you do it for, I don't know, Di-Perna-Lyons type vector fields?
Yeah. I mean, as far as I know, if I want to do this, so this is kind of one of the key part in all the techniques we're doing for mixing, at least. Yeah, the Perna-Lyons fields, I don't know how to do these kinds of flows. They're not really differentiable, so d-phi doesn't really make sense. And there's, that's the main issue. I can't use these kinds of Lagrangian techniques. There may be ways to do it, but I don't know.
You were mentioning strong Feld.
For the velocity field, no, that should be okay. I think for Navier-Stokes to be Strong-Feller, you could pose it in W11, and it's fine as long as the noise. Yeah, that's totally fine. Yeah. If you pick initial data in W11, it should be okay. Yeah.
For instance, like you
had an example with four matrices, for vector fields.
Yeah.
There you could imagine them not to be smooth.
Yeah.
And in current state you cannot apply your results, I guess.
No.
I see. Okay.
Yeah. Although the equivalence theorem,
yes,
this one is more likely doable in a de Bernoulli setting. I can't say where.
Okay.
Yeah, here. This, whatever. There's a condition I wrote, which I can't remember where I put it. Here. This one. This comes out, I mean, this is a very simple commutator estimate on the equation. So that gives you the H gamma. I think if you were more clever, you could work in a rougher setting, and you maybe don't really need Lipschitz here. So this type of theorem doesn't require regularity in the velocity, really.
Other questions? It's not to be the case, so let's thank the speaker again. So welcome back. The last lecture of today is the second lecture by Franco Flandoli. Okay.
Thank you. Thank you. So you remember that some messages from the first lecture were that additive noise restores uniqueness in certain equations, but presumably not in the three-dimensional Navier-Stokes equations and not in other relevant equations of fluid dynamics. I started discussing the transport noise, which at least in the case of linear transport equation is very effective, very powerful. But for nonlinear problems, it doesn't work at all, I would say. I didn't find any example, and therefore I move to a more sophisticated noise that will go in the direction of small scales, but not necessary. Namely, there are two categories of sophisticated or more difficult noise, non-trivial noise. One I will call just rich, and the other rich and small scale. The rich and small scale is the most powerful, but just rich is already quite strong. And maybe in the future it's possible that we understand that this just rich works well for more problems with respect to what we understand now. So now, the Brownian before, you remember when I used either as an additive noise or as a transport noise Brownian motion, it was just a d-dimensional Brownian motion, a vector of independent Brownian motions, no space dependence. Now I introduce a random field which is made of Brownian motions multiplied by vector fields. So this sigma k are vector fields, always divergence free, always smooth. This is not the point, not the smoothness. The sum very often is just on a finite number of components, but then in some limit is necessary to consider infinite number. And the wk are scalars, so the vector w is a vector field like velocity, the meaning of velocity, and w are scalars, so the Brownian motions just multiply, so to speak, by plus minus 1 this sigma k at random. And the two-point correlation function in space, so freeze time 1, the two-point correlation function in space is immediately computable to this one. Is an easy exercise. If you replace the sum here, forget about the tensor product that just confused the idea. Take components, component I, component j. When you do the product, there is a double sum, but in the double sum, the terms with different k and k prime disappear because they are independent. I forgot, it's written here, independent. These Brownian motions are independent, so the expected value of the product is the product of expected values, and among the properties of Brownian motion, there is that is central. entered, the expected value is 0. So only the terms with the same k remain. The expected value of the Brownian motion at time 1 is 1, so there is no factor coming from the Brownian motion. There is simply the tensor product of the sigma k at positions x and y. And so, this one is the covariance in space, which is a matrix. Very often is space homogeneous, namely it is very often it will be a function of x minus y. When it is, I will maybe write a Q0 to have to be precise in the notations, but not necessary, so not necessary. And the diagonal plays a special role. So you have to think that it's very important to focus on the diagonal, which in the space homogeneous case is Q0 at 0. So is constant, independent of space, and on outside the diagonal. Okay, so these are two objects in which we have to concentrate on the diagonal and outside the diagonal. When I say rich noise, means that this is not trivial, namely it's not just a Brownian motion without space dependence. There is a non-trivial dependence on space, which one way to formalize this non-triviality is by Fourier transform. In this case of space homogeneity, you do the Fourier, you write Q0 of x in Fourier, and so let's say that you introduce the Q hat of psi, so to speak, and for this spectral measure, if we assume that this is strictly positive on a set of positive Lebesgue measure, then this is sufficient for the non-triviality. So there are many Fourier components active. The other case, small scale, rich and small scale, means that these many Fourier components have to include, or maybe just include, highly oscillating components, so high frequencies. Small scale from the viewpoint of space. And just rich was sufficient to prevent a special blow-up phenomena for point vortices. And so let me first speak of this, because maybe it has other application that we didn't realize, so it's important to know this phenomenology. So I write again, as in the first lecture, the dynamic of point vortices with the Biot-Savart kernel, and here I recall three famous results when these intensities, circulations, are all of the same sign, all positive, for instance, there is no collision. So, of course, we start from different initial conditions, okay? So the problem is whether these points may collide. When they collide, the kernel is singular, becomes infinite, and the system loses meaning. Maybe there is a continuation, but this is an open problem, and so some people here are working on the continuation, but it's a very difficult problem. So if there is a collision, in principle, the system is a blow-up. And no collision for the same sign, no collision for almost every initial condition. Almost every means that assume that this is up to, assume this is up to n. There are n particles, so take r. If it is on, we always work on the torus, so I should write the torus, but so it's better to write the torus because I want to speak of the Lebesgue measure. So let's say that we have the torus T2 for a single particle. We take n particles. On this, we take the Lebesgue measure on this set, and by this Lebesgue measure we select almost surely the initial conditions. Okay? If we do so, almost surely we don't see collisions. And this is a very important property for the sequence. And but in general, there are counterexamples. I don't write the details of the counterexamples, but if you take 3 vortices in a certain position, triangular positions with certain intensities, they have to be with a positive and a negative at the same time intensities, this triangle moves, rotates in a self-similar way. After a while you see it like that, and in a finite time it blows up to a single point. So maybe this one after a while, and it blows up in finite time. And these are 3 important phenomena. And another piece about deterministic point vortices, I learned from a paper of Poupeau, suggested me by Luigi, by the way, some years ago, and sometimes it's called the Choquet symmetrization trick. If you take the empirical distribution of these point vortices, this is a solution of Euler equation, but is necessary to interpret Euler equation in a very weak sense, a la Choquet, namely first from the classical vorticity equation you integrate the nonlinear term against the test function in a classical way, but it's still not sufficient when omega is a measure like delta Dirac. Then express u by the Biot-Savart kernel, so omega appear, the measure omega appear twice, but still this to measure weight the diagonal. I mean, here you see there is a singularity of k, but then if you notice that you can reverse x and y in this integral in a clever way, you can rewrite in this way, where in place of the Biot-Savart kernel appears this new function, which is the Biot-Savart kernel. Biot-Savart kernel times the gradient becomes Biot-Savart kernel times the difference of the gradient in 2 different points. If phi is smooth, this difference is infinitesimal when x and y are close, is infinitesimal of order 1, which cancels the singularity of the Biot-Savart kernel, which is of order 1. And so this function is bounded and smooth outside the diagonal. Okay? And thanks to this trick, you can put here measures like delta Dirac until blow up. When there is blow up collision, then there is a problem. But before collision, you may give a meaning to this. And so this is just to say that point vortice is not only ODE, but is also PDE. Very important, because now I put noise. If you want to put noise on point vortices, the trivial way, suggested for instance by Alexander Chorin for purposes of numerical computations, is to add a noise to each point vortex. So the point vortices move, dance around each other by the usual motion of point vortices. In addition, they have a little Brownian motion, independent each one. Yes, but this is not a solution of a PDE. It's not a solution of PD. Only in a certain mean field limit it becomes solution of Navier-Stokes. But as a finite system of point vortices perturbed by independent noise, this is not solution of a PD. There is another noise such that is solution of a PD stochastic, of an SPD. Let's start from the stochastic PDE. The stochastic PDE is the Euler equation with this Stratonovich noise, the same noise. It is the same noise that I have used in the linear transport, but now the noise is rich, so to speak, and the motion of point vortices is very coordinated with this new noise. Namely, there is the old interaction plus a term which depends only on the particle. So point vortex I receives input from the noise, but the noise is the same for same noise for all particles, the same. So it's not independent noise for each particle, but the same noise, sometimes called environmental noise, which acts on each particle. So you see that if this noise is rich enough, it acts on each particle the same, but maybe it gives inputs to the different particles which to some extent are a little bit not independent, but with some degree of hypoellipticity. At the end of the story, this is technically the proofs are based on hypoellipticity of this noise. What happens? This is by comparison the case of point vortices with just additive independent noise. So this case is much more difficult from the viewpoint of analysis of point vortices with respect to this one. This is much easier. This is more difficult, but corresponds to an SPD. This one does not correspond to any partial differential equation, just for 20 point vortices. And so for this model, we have the following result. The result was proved for point vortices with Massimiliano Gubinelli and Enrico Prioli, just 1 year after the paper we wrote on transport equation by noise, because we insisted to try to use this transport equation on nonlinear problems, and the only nonlinear problem where it succeeded was this point vortices, changing the trivial noise into a space-dependent noise with some hypoellipticity. Later on, with François Delarue and Dario Vincenzi, we understood better the kind of noise that works. In the paper with Gubinelli and Priola, the noise is not concrete, namely we have proved the genericity result, namely the set of sigma k which work is generic in a suitable sense, so it's very abstract. But with Delarue and Vincenzi, we understood this idea of the spectral measure, the properties of the spectral measure, which implies, so one can produce concrete examples of noise which work. Okay, the paper with Delarue and Vincenzi was written not for Euler point vortices, but for Vlasov-Poisson 1D, which is a system two-dimensional like point vortices with similar Hamiltonian structure, but the noise works for both. And so at the end of the story, the result is that there exists noise such that the particles never collide. So collision is prevented by noise. The blow-up is prevented by noise. And the secret, explained in these 2 lines, even if it is a little bit vague, the intuition is that you start from a deterministic initial configuration of point vortices. Immediately, due to noise, this moves into a typical configuration, one of the infinitely many typical configurations with respect to Lebesgue measure. By the way, the Hamiltonianity of the system is preserved by that noise. So that if you consider the finite dimensional system of point vortices, which is Hamiltonian, you to put this environmental noise is still Hamiltonian in a stochastic sense, so it preserves Lebesgue measure. You start from a deterministic condition immediately, even if this deterministic condition in principle could be outside the full Lebesgue measure set of well-posedness, you go immediately inside, and it is here in this immediately that we use the theory of hypoelliptic operators, hypoellipticity, a sort of smoothing, so to speak, even if the noise is degenerate. The big difference between this noise and this noise. This one is non-degenerate. If you think to this system as a system in the in the torus multiplied many times, this noise is a noise acting on all Fourier components in this huge dimensional space. But this one is degenerate. This along the diagonal is completely zero. So it's a degenerate noise. In spite of that, is hypoelliptic, and so it spreads the measure like a non-degenerate noise, reaching the full Lebesgue Lebesgue measure set from where you don't have singularities. Of course, it's a very heuristic way of describing a relatively, not so long, but a difficult proof, because we have to use Magliavin calculus for singular drifts, etc. So a number of technical things to prove the result. But the principle is this one. When you have two ingredients, one ingredient was the deterministic one of solvability for most, not solvability in the sense, no blow up for most initial conditions. No blow up for most initial conditions. And a noise which spreads, then clearly you go in the direction of having no blow up for all initial conditions. Okay?
Sorry, Franco.
Sì, dimmi. Certo,
Just
certo.
to have a clearer
Right.
picture.
Right.
So here you have two different ways of putting noise in the system. One is in some sense more degenerate than the other.
Right.
What makes...
You mean these two?
Yes, these
ways?
two,
These two?
exactly. So perhaps what are the properties in the two? So you mentioned several properties in the first case, like preserving Lebesgue, etc.,
Right.
which I guess you don't have in the second.
No.
Okay.
In the second.
And is there any physical intuition for which one should?
No, maybe you have also in the second that the Lebesgue measure is preserved because Brownian motion essentially, white noise essentially preserves Lebesgue measure. So
okay.
I don't remember, I should check. Anyway, here it is much easier to prove that no collision happens. So it is true also here that there is no collision.
Uh-huh.
So the property of no collision here is just more difficult than the property here, but it is a PDE property. So it is, I forgot to underline this, at the end is a non-singular, a no blow-up property for the PDE, because it means for very special solution of the PDE. For the solution of the SPD that are concentrated in delta Dirac points, this solution continue forever. Without noise, this solution may, after a finite time, blow up.
Okay.
So these are solutions of an SPD that do not blow up due to the noise. If you take this model, it's just an ordinary differential equation.
Yeah.
So if you want, this is an example of ordinary differential equation in which, thanks to noise, you avoid the singularities.
Okay. And what's your intuition? I mean, there are several ways to put noise in an equation.
Right.
What's your intuition of the difference between, because from many properties in the end are the same, even though perhaps are more complicated to prove or so. What's the intuition? How do you imagine these two situations?
At the PDE level, as I anticipated, my intuition is that these are the large scales of the fluid, and these are small scales which affect in a transport way the large scales, act on the large scales. This is my intuition about that. If I move to here, to point vortices, interpreting point vortices like large scales, okay, maybe if you, maybe, but it's a little bit weaker. And here is, I don't have any intuition. This is just a numerical method of Chorin to approximate Navier-Stokes if you send the n to infinity and take this like 1 over n and the initial condition which approximates the initial condition of Navier-Stokes. So I don't know the physical meaning of this. The physical meaning of that is, okay, little bit and waving. At this level, no. At this level, I strongly believe of the physical meaning. If I put at this.
Okay.
The word environmental, many people like the keyword environmental noise, so now the literature is full of papers on environmental noise, but not for fluids, for other examples, for instance in mean field games and other systems. So people believe that environmental noise is interesting in many applications, except fluid. Now I was discussing fluids only. So
and in this context, what are the assumptions that you have to make to get hypoellipticity?
As I said, if you write the covariance, assume that the covariance of the noise is, sorry, where it is, I hope here, assume that the covariance of the noise is space homogeneous, write it in Fourier, so integral E, etc. in xi, take this Fourier transform and assume that this Fourier transform is strictly positive for xi in a set lambda with Lebesgue measure of lambda strictly positive. So if it is, yes, so you need many Fourier components. You need to activate the system by many Fourier components. So this is essentially the property. Hypoellipticity comes from that. Maybe even less. There is sufficient condition for this hypoellipticity.
And technically then, sorry, last question. Then you said you use Machiavellian calculus?
The Machiavellian calculus is to prove the following, that, where is the stochastic equation? The stochastic equation.
So hypoellipticity enters only in Machiavellian calculus or also through? Only
in Machiavellian calculus, I'm not wrong. Take the law, the probability measure of the vector xt. Xt is the full vector with the different point vortices. In the two cases, what you want to know is that this is a probability measure on the torus. This is a probability measure on the torus T2n. Starting from a deterministic initial condition, so the initial condition, let's say x0 is deterministic, this xt is random, it has a law on this, you want to know that this law is full, essentially. In this case, is not trivial, but, I mean, it's not trivial because k is singular, but otherwise is essentially trivial. In this case, it requires Machiavellian calculus. We have used one criterion from the book of David Noilard. We had to approximate this, to smooth this in order to apply certain criteria and then to make a proof which takes care of the smoothing and other things. So this is the role of the hypoellipticity is to have that the solution at time t has a full law on the phase space. And this is true when you have a sufficient number of this sigma k. Yes, so there is a little, I notice now that there is a little technical discrepancy in my description. Namely, when we in the paper with De La Rue and Vincenzi, in which we had this criteria, is a paper on full space. When you work in full space, instead of the notation sum over k of a finite number of components, you have to use another mathematics because you need Fourier transform and not Fourier series. So sorry, I always used in my lecture the Fourier series because I am on a torus. And then here I wrote a condition in Fourier, there is I admit that I made a little confusion about that, but I hope that the message remains, even if I forgot that I was mixing two different setups. Well, and with probability 1. Okay. And so I already remarked that this is probably a general principle, let's say. I don't have a general theorem, but it may be a principle that should be tested in other examples. And very important is this one. I think historically, if I'm not wrong, that before that paper, before 2011, if you discuss by what is regularization by noise, with some people they mean restoring uniqueness. From that paper, they started the idea that maybe could mean prevent singularities or delay blow up or prevent blow up. Okay, and this was a change of viewpoint, for me essential, not secondary, essential change of viewpoint Okay. However, for many years we didn't have any other example except these point vortices. Perhaps there was an example by David Barbato, Benedetta Ferrario, and Akima Bessai on an alpha model with transport noise, in which they restored some property. So I don't know. That could be that, but okay. Okay, so maybe there is always some other paper around, but okay. Let's go back to Euler equation. And we ask now, strong with this example of the point vortices, we want to understand if a noise here may give special properties from the viewpoint of regularization. Okay, but since at the same time I moved from uniqueness to preventing blow-up, the two-dimensional case is not a great field for preventing blow-up. So in the last one of my lectures, I will treat the same equation in three dimensions, and try to discuss how noise for the three-dimensional Navier-Stokes in vorticity may prevent the blow-up. There is a theorem, a rigorous theorem about that. So, concerning regularization by noise of transport type on fluid dynamics, last lecture I will do something in 3D. But if I put 3D today, it's too early with respect to the stream of things I want to discuss. So I keep 2D. For 2D, I don't have to prevent any singularity in 2 dimensions, but I will explore another property due to noise in this position, which is a property of dissipation. So instead of regularization, as I said already in the first lecture sometime, regularization / dissipation. I don't know. And everything is, I strongly need to say that Lucio Galeatti was the person that during the master thesis discovered a wonderful trick, also maybe with the help of David Barbato, and from that we were able to do a lot of work on this idea. So I'm going to describe this idea. As is written here in bold, I will illustrate a dissipative property, not a regularization by noise. Philosophically, it's the same because when we apply to Keller-Siegel or to nonlinear heat equation, it becomes the same, exactly the same mathematics becomes delaying blow-up, delaying or preventing blow-up. And also the three-dimensional Navier-Stokes that I described in the last lecture. But for two-dimensional is not preventing blow-up, is another property, but is the same concept. And I think is very important concept. So the outlook is the following. I will take two-dimensional Navier-Stokes on the torus, perturbed by this transport noise, non-trivial noise. I want to prove an extra. I put a little viscosity technically because I prefer for proofs. Some result also without this viscous term, but I prefer it. So there is a little damping, but there will be an extra energy dissipation due to this noise. This is the main concept. Due to this noise, we have an extra energy dissipation instead of regularization. The noise is the same as before. Two ingredients will have this noise. One is that on the diagonal the covariance must be rich, must be positive, and the second is that the sigma k have to be rapidly oscillating, small scales. So it's not like the example of the point vortices, which in principle doesn't need small scales. Here we really need the small scales, and it's here that perhaps we get close to other theories in which rapidly oscillating fields are used for other purposes. But here there is a key point. I have to explain why a term like that produces dissipation. Oops. Okay, now first this slide is the next one. Sorry, I anticipated the slide. So first this slide, which is also important. This kind of transport noise is like the other transport, namely it preserves any function or large class of functions of the vorticity, in particular the entropy. So at the level of vorticity, there cannot be dissipation. The dissipation is if you go in negative Sobolev norms, as it was done a second ago by Samuel and others for the mixing problems. So if we go, so the dissipation is for the kinetic energy, not for the entropy. And let me first state the theorems, two theorems. The first one is more theoretical. It works without this viscosity, also with viscosity, but in the paper was proved without viscosity. Then, since we have later papers, we know that it works also with viscosity. It says that if you take Euler equation with this noise and you build a sequence of noise of this form constructed in a suitable way, then the solution of the Euler converges to the solution of a Navier-Stokes, deterministic. This is stochastic, this is deterministic, and there is a convergence from the stochastic to deterministic if these noises are suitable. The properties of the sigma n, as you will see when I go into proofs, etc., are to be smaller and smaller scales. If sigma n are smaller and smaller scales in a suitable sense, the Euler equation stochastic converges to the Navier-Stokes equation. The same if there was already a small viscosity. I call nu T turbulent viscosity this one. Turbulent viscosity in honor of Joseph Bouzinesque, who understood that in fluids the small scale turbulence may have an effect similar to dissipation. Oops. And as you know, in the theory of large eddy simulation, it is very common to add these terms to describe the effect of turbulent small scales on large scales. But I mentioned a second theorem. Sorry, I'm making some noise with the slides. A second theorem is more or less, let's say, same setup, but here I prefer to have already a small viscosity from the beginning for the strength of the result, quantitative strength. So same setup, but more quantitative estimates. So the n, if we go at the level of momentum, so in particular computing the energy, the difference between the velocity fields in L2 norm is small, is controlled by essentially the length scale of the noise. So I said that the sigma k is a sequence of sigma k which have smaller and smaller scales. If you introduce properly the concept of length scales of this sigma k, this length scale controls the energy, and so the solution of the stochastic problem is close to the solution of a very dissipative Navier-Stokes in energy is close, and so the kinetic energy of this is small. The kinetic energy of this time t is small because it's close to the one of a very dissipative problem. Okay, so there is a dissipation of kinetic energy in an average sense. And this is the important message that I would like to compare with convex integration, but of course it's very difficult. Very difficult. Since the key of this theory is the fact that forget about this if it confuses the idea, is the fact that this transport noise is equivalent to another noise, which calling it transport is strongly misleading, but is still a noise in multiplicative form. You see there is a difference in symbol. There is this symbol which is called the Stratonovich and another symbol which is called Ito that I'm going to explain, plus an elliptic operator that didn't appear here, divergence of this covariance gradient. If I tell you that by a mysterious Stratonovich calculus this object moves into this plus this, I think it looks a little bit tautological, is how to say. I take a problem with an additional viscosity, I make some trick to show that this Ito is small, and I claim that this is a result for a transport equation. So I need really to convince you that this problem is equivalent to this one. My friends that do stochastic analysis, they say, you don't need to convince anybody. It's mathematics, the Stratonovich is the sum of Ito and that. For me, I'm strongly pressed myself to find intuitive explanation of these facts beside the formal rules of stochastic calculus, and so I will give the intuitive, deepest explanation that I know of the fact that a transport term can move into a parabolic term plus fluctuations. So the key point, you know probably from homogenization theory that is known that first order differential operator, when you rescale the coefficient, could converge to second order differential operators. But here is more precise in a sense. This first order differential operator is equal to a second order differential operator plus fluctuations. And the analysis of these fluctuations not only can show that they go to zero in certain limits, but you can estimate them quantitatively in a very concrete manner. So quantitatively, this I think is slightly superior to the usual homogenization techniques. And the deepest explanation I know of this fact is the following. First, the noise that before was denoted by time derivative of a Brownian motion, now is replaced by a stochastic process, but smoother. You know that Brownian motion is not differentiable, so this time derivative is a distribution in time. In space is not terrible because it's a finite sum of coefficients, but in time is a distribution. I replace by a smooth, I mean not super smooth. I mean, at least is a function. This process is at least real valued, not distribution valued. That approximate the Brownian motion. For instance, this is the typical proposal to make things easy. An Ornstein-Uhlenbeck, namely a process that has, if you start somewhere, there is a damping due to this 1 over tau, and then there is the action of the Brownian motion, which put again energy into the system, but this energy is also continuously damped, and so you have a system like that. So there is a time scale tau of correlation of this process. The time derivative of Brownian motion is so-called, this one is so-called delta correlated in time. This one is tau correlated in time, so has a finite correlation length in time. From the viewpoint, okay, let's stop here about, there are of course many other comments that one could add, but so this is a typical way to approximate white noise. This is white noise, and this is a typical way of approximating white noise with a finite time correlation. And when I have finite time correlation, I can play a little bit, and this is the key trick. I take this term, this first order operator that I have to understand, and I delay the time in in omega, not in the noise, in omega. And of course there is this additional term with the increment of omega. And then I replace the increment of omega by the equation, because the increment of omega in time is equal to, and so I replace with what is written here. I already made some manipulation, but very easy. So the term in which I just delayed omega is the fluctuation. I call it fluctuations. I call it f and report as f below. This term with the increment of omega, you see there is a gain. So there is an eta here, which appears also here. So you see this eta is this eta. And theta is this theta. And when I take this term from the time increment of w, I have the other two. This one is this one, and this other is this other. Okay, you see. Then here is just rewritten, and then I do the following. I prefer to have, instead of this omega s, which is integrated, here there is a ds missing. Instead of this omega s, I prefer omega t, so I introduce an additional term, and the other is below here. The rigorous analysis of these two remainders is very difficult, but intuitively, if you concentrate a few minutes, you arrive to the handy conclusion that this term is much smaller than this one. This is natural because this was omega s, I replace omega s by omega t, and the difference, so there is a difference more than here. This one is more difficult. Understanding how small is this term is more difficult, but if you take the expression of f and you think a little bit, you realize that probably this is much smaller than f because it's similar, but here there is a small time interval that was not inside that one. So essentially, I delete these two. Rigorously, these kind of computations are very difficult. Umberto Papalettera, that is not here, wrote the PhD thesis on this topic, writing several papers on this topic, trying to make rigorous the fact that at the end only the fluctuation term and the second order term remain in the limit when tau goes to 0. But up to the rigor is clear. There is a fluctuation term and there is a second order term. To be more precise, so heuristically we decide that this first order operator is approximated by this delayed first order operator and this second order differential operator, where the matrix Q, or it would be maybe better to say 1/2 Q, for comparison with the final result, is given by this integral. And now the intuition, which is also part of the rigorous results, is that this term converges to Ito. Of course, you have to integrate it, not pointwise in time. If you integrate this f in time, you see it has the structure of Ito integrals. Ito integrals, the Ito integral of a process in dw is approximated by the sum of the process computed at initial time of the partition times W at the final time of the partition minus initial time. So this x is computed at the initial time of the increment, which is precisely what happens in this expression. You have eta is like the increment of W, omega is like the integrand. The delay is precisely the one which produces itosense. And more sophisticated is the fact that this object, which is still random, because eta is a stochastic process, converges to a deterministic quantity. The fact that something random like that converges to a deterministic quantity is not a trivial result like low or large numbers. It's more sophisticated, is related to the concept of quadratic variation. In the case when eta is the Ornstein-Uhlenbeck written above, is an exercise of 1 or 2 pages of computation with expected values. So it can be done. So this quantity converges to a deterministic, always integrated, converges to a deterministic quantity that is precisely the covariance of the noise along the diagonal times the length of the time interval, like the quadratic variation of Brownian motion, which converges to the length of the time integral. There is a 1/2 coming out from a detail that I don't want to discuss. And so at the end, this is the explanation why this first order operator in the limit when tau goes to 0 of delta correlated noise produces these two terms, apart from the Ito-Stratonovich calculus, which may be a funny part of mathematics for strange people. And therefore, please accept that this totally hyperbolic first order problem, or with a small viscosity, is completely equivalent to this kind of problem. And now, this was a block, a logical block, to accept that when I study this problem is like to study this problem. Now let's go back to the main question of convergence to deterministic Navier-Stokes, because here we have the correct deterministic Navier-Stokes piece. This will be the turbulent viscosity. But still here we have the Ito integral, which is not zero. So we want to maintain here this additional dissipation. So we want that this diagonal is strictly positive, to contribute to the other dissipation. But at the same time, we want that this Ito integral is small. We cannot hope that is small in the L2 norm, because the smallness of this in the L2 norm would correspond to the fact that omega itself dissipates. And you remember a slide in which I showed omega is preserved without this nu. Without this nu, omega is completely preserved. It's an Euler problem. But if we weight this in negative subole spaces, this could be small, and this is the point that I want to discuss.
Sorry.
Yes, please. Dove devo?
The slide più in basso.
Before?
Yes. Okay. Yeah, there. Wait. So the no. Okay.
Okay.
There.
Okay. I understand.
Yes.
Now.
So at the beginning we had, if I'm not mistaken, U prime times gradient of
yes, I always
omega, right?
I always wrote U prime gradient of omega.
Right.
Yes.
Where U prime is are the small scales.
Thank you.
Right.
Thank you. So I completely forgot to say a basic conceptual sentence, namely, we have the true Navier-Stokes. We manipulate to write U prime, etc. Then I destroyed the true Navier-Stokes, neglecting the commutator. You remember that there was a commutator away. And then I destroy again by replacing U prime, which would be through small scales of the fluid, and instead of that I put a stochastic process.
Okay, which works, I mean, it is constructed so that it works at small scales too,
At
right?
small scales.
Now, the question is, why do you, okay, maybe, surely you said it before, but you put Stratonovich there, and then you say, okay, but doing all this machinery, we can get equation with an Ito formula. So why didn't you put at the beginning like above, like instead of substituting that U prime dot nabla W with that Stratonovich integral and then derive a stochastic, an SPD with Ito, why didn't you put immediately like an Ito term? That creates some problems?
It's completely wrong. It's completely meaningless. Precisely this description shows that if instead Brownian motion, white noise are idealization, like delta Dirac. So let's start with something which is less idealized, more realistic, and let's do the computation. Okay. And from the computation, we end up with the equation written here. So this is the correct equation. This equation can be reinterpreted as a Stratonovich.
Okay, so the correct like noise to put is in a Stratonovich sense.
Right.
Right.
There is absolutely no doubt.
Okay.
By the way, there are also negative theorems like that. Forget about the nonlinearity. If you take the heat equation with the Ito noise, is not well posed, unless this viscosity is large enough. You need a link between a coefficient, call it B, a coefficient in front here. You need a link like nu greater than B square over 2, something like that. It's well posed only under a super ellipticity condition. So the parabolic equation with Ito noise are bad, are wrong, so to speak.
Also
so
in a physical sense.
Physical sense are completely wrong.
Okay.
Mathematically you can write them, but you have to impose a super ellipticity condition to solve them, which is a clear signature that something is wrong. Physically, completely wrong. There is another way of explaining Stratonovich, of course, people in stochastic know very well, which is the so-called Wong-Zakai principle. There is something called the Wong-Zakai principle. Which is called principle and not a theorem because it's really a principle. It also always, which is that if you approximate white noise by smoother processes, you converge to Stratonovich. And indeed, what I showed in the previous 2-3 slides was one of the possible approaches to this Wong-Zakai, the approach that, in my opinion, is the deepest one to the Wong-Zakai, to understanding Wong-Zakai. Also, probably the approach that I described could work without probability in some deterministic context related to homogenization, etc. So I think it's quite deep, even if it was very heuristic in the way I expressed it. And so there is no doubt that this is Stratonovich and that this is the correct interpretation. By the way, for instance, with Stratonovich, which you have the usual conservation law, if I put Ito, I break all conservation laws. So it's completely wrong. Completely wrong.
You need that additional term.
Yes, there is. Exactly. If you start with Ito, you have a negative viscosity here, the same term but negative, which breaks all physical sense, etc. So Stratonovich is out of question the correct choice. And the question, as you remember in the previous slide at the end, was controlling the fluctuations, the Ito fluctuations. But this is a little bit technical. I decided that probably I would arrive to this slide when all of us are cooked, and so I will not manage an Ito integral in a negative Sobolev space, but I will do the following, which is, as it was remarked before by Samuel, for the concept of mixing is more or less two ways of seeing the same. Instead of measuring negative Sobolev space, you measure against the test function, okay? Against the test function, and then I take the square and expected value. So I want to show that invariance against the test function, it is small if I take the noise with certain properties. I want, or if you want, let us explore together which properties of the noise make this variance small, okay? First, Ito calculus, so the first step, the first equality here is just integration by part, because I put the phi inside this scalar product inside, and then I integrate by part the operator sigma k grad. The second step is Ito calculus. The expected value of a sum of a stochastic integral, fortunately, is the sum and not the double sum. Again, because these are independent, and among the rules of Ito integrals, there is this one. So only one sum remains. Only one. There is here. There was a square. Sorry. Oops. Even if there is a square, the square goes inside with only one sum. And now the question is computing the square of this scalar product with the sum. So the sum of these scalar products are integrals. Is the scalar product in L2, so integrals. Integrals in dx dy. So double is a double integral. Here there is no, I mean, it's not reduced to, so it's a double integral, not a single integral, with the, for instance, sigma k x, sigma k y, etc. But the point is that the sum over k over sigma kx, sigma ky is q, is q. So you recondense these terms into the covariance. So it is the covariance, which is a matrix, applied to these two vectors in x and y, and multiplied by these two scalars. So it's very elegant computation. If I did the computation in the negative Sobolev space, is not elegant at all. But with the test function, is very elegant. Now I introduce the best constant, which gives this inequality. So I have this covariance is a positive definite. So I do this, and I look for the best quantity epsilon q, which produces this inequality. And so if we call epsilon q this, you see from this line, collecting this line, I don't know where it is, I'm sorry, it is, we are here. So we started, let us recall, we started from the fluctuations, the Ito integral, against the test function square. Ito calculus, manipulation of this, this is still definition, sorry, this is just a recall from the previous slide to arrive to the following conclusion. This is the conclusion. So this is the conclusion. So the variance of these fluctuations is controlled by two things which are not small, and t is not small, but there is this constant epsilon q, which may be small. So we have to understand when this epsilon q is small. And I will do tomorrow morning. So now I only collect the idea qualitatively without any more computations. So we arrived here. This epsilon q, you will see, is small if the noise is made of highly oscillatory fields. More higher is the frequency of the oscillation, smaller is this constant epsilon q. But we can make this epsilon q as small as we want by oscillation, still preserving on the diagonal the value we want. So we can keep the value of the diagonal given a priori if we want, and have that by the high of oscillation of the fields which compose Q, this is arbitrarily small. And we can reformulate this either as a theorem, scaling limit theorem, when a parameter n goes to infinity, or as a theorem on estimates of the difference between certain fields and other fields. Quantitative estimates of the difference. So summary and outlook, just to remember where we want to go. I will try, but I already said from the very beginning that I don't have great intuitions and results. It's more to push also the discussion on the link between regularization. Sometimes instead of regularization, you see today I speak only of dissipation by noise. Only the last lecture will be again regularization in 3D. And convex integration and spontaneous stochasticity. Unfortunately, I start from two different formulations, and this is a drawback. In this formulation, I put the small scales here with randomness. In convex integration, we put the small scales here in a deterministic fashion, and we try to exploit what is going on. Jump these, which we already know. I didn't complete the proof. I said I do tomorrow morning, but essentially we have understood that small scale transport noise, I added this sentence because is a noise which is vorticity preserving. So it's a noise which is vorticity preserving but dissipates energy. But here arises a question which will go in the direction of convex integration, namely that maybe there could be fluctuations of this process. Think to the Brownian motion as plus minus against this. There are these fields which are rapidly oscillating, and each one of these fields is multiplied by plus minus. Assume that now for a while there is an anomalous sequence of plus with these oscillating fields. Maybe we go in the direction of something which was understood by the theory of convex integration. So it could be that convex integration captures some phenomena which are extreme events of what I'm discussing, even if apparently is not. It is the last slide. Thank you very much.
Are there questions?
Okay, too tired. Fortunately, there are no questions. I will not be able to answer.
Yeah, what is the convergence of your main results towards Navier-Stokes, but with VT, right? What is the sense of convergence?
Convergence. We had two papers. The first paper, it was weak convergence against nest functions, weak convergence. In the second paper, it was quantitative. So, for instance, in any Sobolev norm immediately below L2 in vorticity. So, vorticity in L2 is preserved. But if you take any Sobolev norm H minus epsilon, we converge in this H minus epsilon, including convergence of velocity in L2, which is the physical result. The physical result is the convergence of velocity.
Also, usually the limit equation, so if you put in a weak space, they don't have uniqueness, so right? So you have like you have a convergence of subsequence, or you have all convergence.
No. It's convergence of the full sequence. This is not. I mean, I stated two theorems. The second one is quantitative, and from that theorem you understand it's full sequence. But also from the fact that the limit problem is deterministic. When in probability you have subsequences which converge to no, sorry, it's not that because deterministic. The limit problem has a unique solution. So the limit problem has a unique solution. So if you have maybe by the first paper that we wrote was based only on compactness arguments, not quantitative. So we proved that the family of solutions indexed by n was tight, and so there were subsequences which converge, but it converged to the solution of Navier-Stokes, which is unique, and so all family converges. All family converges.
Yeah, thank you.
Converges first in law, and since the limit is deterministic, it converges also in probability.
Thank you.
Other questions? Okay, so I think
Thank you very
thanks.
much.